Hello and welcome, my friend. You have found your way to this quiet corner of the cosmos, a space where science slows down just enough for you to breathe with it, where equations soften into stories and the mysteries of the universe stretch out like a night sky that never truly ends. Wherever you are, maybe you're in a small city apartment, maybe under an open sky, maybe lying still in the half-light of your room. I'd love to know where you're listening from. People around the world tune in from every corner of time zones and continents, and somehow, through this invisible web of signals and sound, we all share one moment together. Tonight's journey begins with a question that has followed humanity since the first flicker of awareness. Does existence truly end? For centuries, philosophers, poets, and physicists alike have stood at the edge of that question, looking out into something they could never quite name. But in the last 100 years, science, and especially quantum physics, has offered a strange, almost unsettling whisper. Maybe the end isn't what we think it is. The phrase, the end of existence, sounds final, almost absolute. Yet the deeper we look into the fabric of the universe, the more we discover that endings don't behave the way our instincts expect. In quantum mechanics, particles vanish and reappear. Matter transforms into energy, energy back into matter, and information, the very pattern that defines a thing, seems never to be lost. That idea alone unsettled some of the greatest minds of modern physics. Richard Feynman once said that nobody truly understands quantum mechanics. Niels Bohr admitted that if quantum theory hasn't shocked you, you haven't understood it yet. And even Albert Einstein, who helped to build its foundation, spent decades wrestling with its implications, especially the possibility that reality might not be local or even singular. To these scientists, what lay beneath the world of atoms was not simple emptiness, but a vast, interconnected field of probability. A place where every event, every particle, and perhaps every thought was entangled with everything else. When physicists talk about this quantum field, they often describe it as a sea of pure potential, the background energy that underlies all that exists. Out of this sea, particles are born, live their brief existence, and dissolve again. But the field itself never dies. It only changes its patterns. Roger Penrose, the mathematical physicist who shared a Nobel Prize for work on black holes, suggested that this same field might even hold the structure of consciousness itself. Along with anesthesiologist Stuart Hameroff, he developed a hypothesis called orchestrated objective reduction. The idea that quantum events inside the brain's neurons could link awareness directly to the underlying fabric of reality. If this is true, then consciousness might not be a fragile flame that goes out when the body stops functioning. It could be a pattern in the universal field, a resonance that persists, much like a note that continues to vibrate long after the instrument falls silent. For many scientists, that thought is thrilling. For others, it's unnerving, a kind of scientific vertigo that forces them to question where the border between self and cosmos really lies. Stephen Hawking, who spent his life studying the boundaries of space and time, often reminded his students that information, the fundamental description of a system, can't simply disappear, not even in a black hole. In his equations, information is conserved, preserved in the vast, slow memory of the universe. If that's true, then perhaps nothing that has ever been you is ever truly lost. And yet, the idea unsettles us because it dissolves the edges we rely on. If existence doesn't end, what does it mean to begin? What does it mean to be a single, separate being when every particle that forms your body was once part of distant stars, and will someday be part of others again? Physicists like Max Tegmark, who explores the mathematics of the multiverse, take this to its logical conclusion. If the universe is infinite and the laws of physics uniform, then there may be countless regions where matter arranges itself exactly as it does here. Copies of you listening to these words, scattered across the cosmic lattice of possibilities. In that vast context, death, too, becomes a local event, a transition within an unending pattern. In cosmology, we see a similar story written on a grand scale. Stars die, galaxies collide, black holes evaporate, yet the total energy of the cosmos remains constant. The forms change. The dance goes on. The end of one star becomes the beginning of a nebula, the seed of another generation. It's no wonder that some researchers quietly admit a kind of awe, even fear, in front of such symmetry. The universe does not seem to tolerate finality. What we call an ending may simply be the continuation of information in another form, a rearrangement of what was always there. When you zoom out far enough, even the end of time itself becomes a matter of perspective. At the edge of theoretical physics, models like loop quantum gravity and Penrose's own conformal cyclic cosmology propose that the Big Bang might not have been the beginning of everything, but rather the latest in an infinite series of cycles. Universes born, expanding, cooling, and giving way to new ones. In that picture, there is no true end, only transformation. From that vantage, the fear that something could simply stop begins to fade. The cosmos appears to breathe, in vast scales of expansion and renewal. And perhaps our consciousness, being part of it, breathes in the same rhythm. The end of existence, then, may be not a wall, but a horizon. A horizon doesn't mark the end of the ocean. It only marks the limit of what you can see. Beyond it, the water continues. Quantum theory shows us that reality itself is like that, an ocean of probability that extends beyond the line of our perception. Each observation collapses a wave of possibilities into the single experience we call now, but the deeper field remains untouched, infinite. That notion has led some physicists, like John Wheeler, to propose a participatory universe, a cosmos in which observers are not passive but active participants, shaping reality through observation itself. Wheeler coined the term "it" from bit, suggesting that physical existence arises from information, from the yes-no questions that underlie quantum events. In that sense, consciousness and existence are intertwined, each giving rise to the other. If that's the case, then consciousness may never truly vanish, because the act of observation, the awareness that gives form to reality, is woven into the universe's fundamental code. You can imagine this like a great mirror reflecting and being reflected endlessly. Each conscious being is a small reflection of the whole, and the whole contains every reflection within it. When one reflection fades, the mirror remains, quietly holding every image that ever was. When you listen to these ideas, let them move through you slowly. They're not meant to convince or convert, only to open the space of wonder, the same space that drives both science and art. The thought that existence may not end doesn't remove meaning from life. It adds depth to every fleeting moment, every breath, every connection. Right now, the atoms in your body are ancient. The iron in your blood was forged in a supernova long before Earth existed. The calcium in your bones was once the dust of a dying star. Every heartbeat is a continuation of that cosmic lineage, an echo of stellar rhythm. So, when physicists speak about the end of existence, what they often confront is not annihilation, but transformation. The question becomes not what happens when it ends, but what does ending even mean in a universe where nothing is ever truly lost? As Max Planck, the founder of quantum theory, once said, "I regard consciousness as fundamental. I regard matter as derivative from consciousness. If that's so, then existence, and whatever we think of as its end, may itself be a construct of awareness." Perhaps this is what terrifies and fascinates quantum scientists in equal measure. That when they peer into the equations describing the smallest scales of reality, they see something that looks uncomfortably like mind staring back at them. And if awareness is the ground of being, then the end of existence could simply be another beginning, viewed from a different angle of perception. When you think about that, the universe feels less like a machine and more like a vast conversation, one that began long before you and will continue long after. Even now, as you listen, photons that left distant stars millions of years ago are reaching the surface of your eyes. Those photons carry the memory of their journey, a message written in light. That existence flows forward without truly ending, that the cosmos continues to whisper through you. The universe, as physicists like Roger Penrose and Stephen Hawking showed, has an extraordinary relationship with time. From our vantage point, time appears to flow in a single direction, from the past through the present into the unknown. But the equations that describe the microscopic world don't require that arrow. They work equally well forward or backward. This symmetry has always puzzled scientists. Why, if the laws of physics make no distinction between past and future, do we experience time as an irreversible current? The best answer so far involves entropy, the slow, steady increase of disorder that gives the universe its sense of direction. Entropy tells us that the early cosmos was extremely ordered, smooth, hot, uniform. Over billions of years, it has grown more complex and diffuse. Stars ignite, burn, and collapse. Galaxies form and drift apart. And in the end, everything trends toward a state of equilibrium. In classical thermodynamics, that ultimate equilibrium is called the heat death of the universe. A time so far ahead that stars have burnt out, matter has decayed, and even black holes have evaporated through Hawking radiation. Only a thin mist of low-energy particles remains, and the cosmos reaches maximum entropy. To most people, that sounds like the end of existence. But to Penrose, it was a beginning. He noticed that at that final, almost featureless state, all physical distinctions vanish. There is no meaningful way to measure time because nothing changes. And, strangely, that description also fits the moment of the Big Bang, a state of extreme simplicity before structure emerged. Penrose proposed a theory called conformal cyclic cosmology, or CCC. In this model, the end of one universe and the birth of the next are not separate events but different views of the same geometry. As one cosmos fades into smooth uniformity, it becomes, through a kind of mathematical rescaling, the seed of the next expansion. Time, in this sense, loops through cycles without end, aeons giving birth to aeons. Within that picture, the end of existence dissolves. Matter transforms, entropy resets, and the information that shaped one universe may ripple forward as boundary conditions for another. Penrose even suggested that traces of those previous universes might still be visible, faint circular patterns in the cosmic microwave background, the afterglow of the Big Bang. Whether or not CCC proves correct, the idea carries a quiet reassurance that the cosmos itself may never truly vanish, only change its mode of being. And this theme reappears throughout physics. When John Wheeler described the participatory universe, he meant that reality is not a fixed stage but a network of interactions. Each measurement, each act of observation helps to bring a potential state into actuality. The universe, in this view, is a kind of dialogue between possibility and awareness. At the quantum scale, this interaction takes the form of wave function collapse, the transition from a cloud of probabilities to a definite outcome when measured. For larger systems, that collapse averages out, giving us the predictable classical world we know. But the boundary between quantum and classical is not sharp. It's a gradient, one that invites the unsettling thought that observation itself may play a role in the universe's unfolding. That idea does not imply that human minds control the cosmos. It simply suggests that information and observation are woven into its fabric, that reality is participatory all the way down. Physicists like Wheeler, and later information theorists such as Rolf Landauer, began to see the universe not only as matter and energy but as computation, processing information through every interaction. Landauer's principle, information is physical, means that every bit of data has a measurable energy cost. From this, the concept of digital physics emerged, a cosmos where the laws of nature act like algorithms, evolving states according to fundamental rules. In that framework, existence doesn't end, it updates. The apparent finality of things is just a boundary between states, the completion of one calculation and the beginning of another. The quantum field itself behaves this way. Even when particles annihilate, the field remains. Vacuum fluctuations continue to spark pairs of virtual particles into brief existence, their energy balancing to zero. To many physicists, this shows that nothingness is never truly empty. In cosmology, this restless background is known as vacuum energy or dark energy, and it appears to drive the accelerating expansion of space. If this acceleration continues, distant galaxies will drift beyond the horizon of visibility, leaving each region of space increasingly isolated. Yet the field that carries them, the underlying quantum fabric, persists everywhere. To imagine this, think of a vast ocean in which waves rise and fall. Each wave is temporary, yet the water remains. In quantum theory, existence itself is that ocean. Waves of probability form the patterns we call particles, stars, and minds. When a wave subsides, the ocean is unchanged. It continues to hold every possibility within it. Physicists find this both beautiful and unnerving. Because if the universe is fundamentally an information field, then the loss of any particular pattern, even the dissolution of a star or the quiet end of a living brain, may not be destruction but transformation. The information may disperse, but it does not vanish. Hawking's final work addressed this directly, the black hole information paradox. When matter falls into a black hole, it seems to disappear. But according to quantum mechanics, information cannot be destroyed. Hawking eventually concluded that the information is encoded in the subtle correlations of the radiation emitted as the black hole evaporates. The process is unimaginably slow, yet it ensures that the record of what once existed remains in the universe's fabric. If even the most extreme object in nature preserves information, then total erasure, the absolute end, may not be possible at all. In this light, the phrase "the end of existence" becomes more a limitation of perspective than a statement about reality. We perceive beginnings and endings because our consciousness tracks change, measuring before and after. But from a cosmic viewpoint, existence is a continuum of transformation, where energy, matter, and information exchange roles endlessly. Max Tegmark expresses this as the mathematical universe hypothesis. The idea that reality itself is a mathematical structure, timeless and complete, containing every possible configuration within its geometry. From within that structure, we experience change. From outside it, there is only the whole pattern. When viewed this way, the universe no longer seems like a story with a first page and a last. It becomes a landscape of eternal relations, every state coexisting, every possibility woven together. You might think of it as a library beyond measure, each book a universe, each page a moment. Nothing is ever deleted. We simply move our attention from one page to another. Even entropy, often described as the universe's tendency toward disorder, can be seen as the expansion of potential, the spreading of information into ever larger forms. The end, then, is not silence, but diffusion, a kind of cosmic exhalation. When cosmologists model the far future, they describe epochs that stretch beyond ordinary imagination. The degenerate era, the black hole era, the dark era. Yet within those calculations lies the recognition that time itself becomes ambiguous. When change ceases, time loses its meaning. And in that stillness, according to Penrose's equations, a new cycle could begin. This recurring theme, of renewal emerging from apparent finality, links the scientific and the philosophical. It invites a gentler understanding of existence, one that replaces fear with curiosity. Perhaps what unsettles scientists most about the end of existence is not the prospect of nothingness, but the possibility that nothingness is an illusion, that the universe might be incapable of ending. If that's true, then the continuity we glimpse in the stars, in the recycling of matter, in the conservation of information, may also echo within consciousness itself. Not as survival in the personal sense, but as participation in the ongoing pattern of being. When cosmologists speak of the end of time, they often use equations filled with symbols that stretch human comprehension. Yet within those equations lies a simple insight. Time may not be a fundamental property of the universe. In some modern theories, time is emergent, a pattern that arises from change, from the relationships between events. Carlo Rovelli, one of the leading figures in loop quantum gravity, describes this beautifully. In his view, there is no master clock ticking somewhere in the cosmos. Time is the way we measure the rhythm of transformations. When nothing changes, time itself dissolves. If that is true, then what we call the end of time is simply the point at which change ceases to have meaning. The universe may continue, but without distinction between past and future, without before or after. Rovelli's work suggests that space, too, is not continuous. It is quantized, built from tiny loops of geometry at the Planck scale. The fabric of existence is not smooth but granular, like a woven tapestry viewed from afar. At this scale, space and time become aspects of the same quantum field, a single entity that flickers in and out of form. When you imagine this, the phrase "end of existence" starts to feel less like a boundary and more like a change in texture. the pattern continues, but our familiar categories, space, time, matter, no longer apply. And yet, even in this quantum foam, order emerges. Just as ripples in a pond organize into waves, tiny fluctuations in that early field gave rise to galaxies, stars, and planets. The same mathematics that describes the subatomic realm also describes the structure of the cosmic web. The universe seems to be self-similar across scale, a fractal unfolding from the very small to the unimaginably large. This continuity fascinates quantum scientists because it implies that the laws governing the smallest particles might also shape the evolution of consciousness itself. After all, the human brain is composed of the same particles, governed by the same interactions as the rest of the cosmos. When Penrose and Hameroff proposed their orchestrated objective reduction model, they were not claiming to have solved the mystery of awareness. They were suggesting that the mind might be part of the same physics that governs the birth and death of stars. In that picture, the boundary between inner and outer fades. The processes that generate thought, electrical impulses, molecular vibrations, quantum coherence, mirror the processes that generate the universe. To think may be to participate in the same creative flow that drives cosmic evolution. Some scientists, like David Bohm, developed this idea into a broader philosophy. Bohm, a colleague of Einstein's, believed that reality has two layers: the explicate order, the world of forms we perceive, and the implicate order, a deeper level where everything is enfolded into everything else. According to Bohm, what we call separate things are simply different unfoldings of the same underlying whole. He once wrote, "The universe is not made of things, it is made of events." If this is so, then the end of existence is simply the folding of one event back into the implicate order, from which new events will later unfold. In quantum field theory, this is more than metaphor. Particles truly are excitations of fields. They appear, interact, and vanish, while the field itself remains constant. Imagine standing on a beach and watching waves rise and fall. No single wave lasts, yet the ocean endures. The pattern of motion continues even when no individual crest remains. In this sense, the fear some scientists express when confronting the idea of the end of existence may not be fear of annihilation, but of continuity that defies human categories. Our minds evolved to navigate beginnings and endings, cause and effect. When physics hints that these boundaries may be illusions, we feel a kind of intellectual vertigo. Yet that same realization can be deeply peaceful. If existence is a continuous field, then nothing is ever truly lost. Every atom, every photon, every bit of information contributes to the whole. The patterns that form us are temporary, but the fabric that holds them is eternal. Consider what happens when a star reaches the end of its life. A star, like our sun, will eventually exhaust its hydrogen fuel and expand into a red giant, shedding its outer layers in a luminous cloud. The core that remains will shrink into a white dwarf, a dense ember that slowly cools over billions of years. A more massive star will die more violently, collapsing into a supernova that for a brief moment outshines its entire galaxy. In that explosion, heavy elements are forged: carbon, oxygen, iron, the ingredients of life. Every atom in your body was created in such a furnace. When you breathe, you inhale the remnants of ancient stars. When you think, the electrical impulses in your brain are carried by ions born in those same stellar fires. Life is not separate from the universe's cycle of creation and dissolution. It is one of the ways the universe knows itself. Astronomer Carl Sagan captured this truth simply. We are a way for the cosmos to know itself. From this perspective, the end of existence is not extinction, but transformation, the reorganization of matter and energy into new patterns of awareness. Quantum physicists often describe reality in terms of superposition, the coexistence of multiple potential states. Before a measurement, a particle's position, momentum, and even existence are spread across probabilities. Only when observed does it choose a definite outcome. The act of observation does not create the particle, but it crystallizes one version of reality out of the many possible ones. At the human level, our perceptions may play a similar role. Each moment of awareness is a collapse of infinite potential into a single experience. When that awareness ceases, when the observer changes form, the field of potential remains. In that sense, existence continues, but our participation shifts. The fear of an ending is replaced by curiosity about what new pattern will emerge. Even the expansion of the universe, which once seemed to spell inevitable isolation, carries hints of renewal. As galaxies move apart, regions of space that were once dense become diffuse, and new structures can form at smaller scales. The dynamics of cosmic inflation, the rapid expansion that occurred moments after the Big Bang, might occur again in distant regions, giving birth to entirely new universes. This concept, known as eternal inflation, suggests that space itself is constantly generating new domains, each with its own physical laws. In such a multiverse, there is no final moment, no last light to fade. The process continues indefinitely, like an infinite tree branching into more universes than numbers can describe. Max Tegmark's mathematical model fits neatly here. All possible structures exist within the grand set of mathematical possibilities. What we call our universe is one particular subset, temporarily experienced by conscious beings within it. When you follow this reasoning far enough, it blurs the line between physical cosmology and philosophy. The question shifts from what ends to what continues to perceive. The neuroscientist Christoph Koch once remarked that consciousness might be as fundamental as space and time, not something that emerges from complexity, but something that pervades reality. Integrated information theory, which he co-developed with Giulio Tononi, attempts to measure consciousness in terms of informational integration, the degree to which a system's parts form a unified whole. While originally designed to study the human brain, the theory implies that consciousness might exist in varying degrees throughout the universe, wherever information is integrated. If this is even partly true, then awareness is not confined to human minds. It is a property of organized complexity, from neurons to galaxies. When complexity changes form, awareness shifts its mode of expression, but the underlying potential for experience remains embedded in the physics of information. In this view, the end of existence becomes simply the transformation of patterns of information and experience. Nothing fundamental is erased. The script of the cosmos continues to write itself, using matter, energy, and awareness as its alphabet. The physicist Erwin Schrödinger hinted at this unity long before quantum information theory existed. He wrote, "The overall number of minds is just one." By this, he meant that consciousness at its core is singular, divided only by the boundaries of perception. Whether or not one agrees with Schrödinger's metaphysics, his statement resonates with the mathematics of quantum entanglement. Entangled particles behave as a single system, no matter how far apart they are. Measurement of one instantly determines the state of the other, as though they share a hidden connection beyond space and time. Einstein called this spooky action at a distance, but experiments have confirmed it repeatedly. In 2022, physicists in Delft demonstrated entanglement across a distance of several kilometers with near-perfect fidelity. The result reinforced what quantum theory had predicted for decades. Reality is non-local. If the universe is a network of entanglements, then separation is only apparent. What looks like distance may be the way a single, unified system appears when viewed from within. This idea offers a different lens through which to see the end of existence. When one part of the network ceases its local interactions, the total system remains. Its information, its correlations, its place in the pattern are preserved in the whole. To quantum scientists, that realization is both humbling and awe-inspiring. It means that the universe may be a single, self-consistent entity that never truly ends, a web of relationships rather than a collection of isolated things. And so, the end of existence is not a wall at the edge of reality, but a transition from one form of relationship to another. When this understanding sinks in, the universe appears as a continuous flow of transformation. Galaxies rise and fade, atoms combine and separate, consciousness awakens and quiets, but the totality, the field of existence, remains whole. The cosmos, from the smallest quantum fluctuation to the largest cluster of galaxies, is a single process. Endless, self-renewing, and profoundly interconnected. If you picture all of this together, the cycles of the cosmos, the self-renewing fields of matter and energy, the way that information persists in every equation, it becomes harder to imagine a sharp border called the end. The universe seems to breathe. Every expansion carries within it the seed of another beginning. Every dissolution releases the ingredients of new form. Physicists sometimes describe the equations of general relativity and quantum mechanics as incompatible languages, yet both insist on continuity. In relativity, energy and momentum are conserved across space-time. In quantum mechanics, the wave function evolves smoothly according to Schrödinger's equation. Even when an event appears catastrophic, a supernova, a black hole merger, the decay of a particle, the mathematics insists that something carries on. The numbers never drop to zero. They simply take new shapes. This continuity is what led John Archibald Wheeler to coin the phrase the universe as a self-excited circuit. In his picture, matter gives rise to observers. Observers, through measurement, give meaning to the universe, and that meaning, in turn, influences the future evolution of matter. Existence becomes a loop, not a line. The circuit may change form, but the current never ceases. You can sense this loop in everyday life. When you breathe in, the molecules entering your lungs include oxygen exhaled by ancient forests, by long-vanished oceans. When you breathe out, carbon dioxide will someday nourish new leaves. At every scale, the same pattern repeats: exchange, transformation, continuation. If existence were to have an end, it would contradict its own logic. The laws that make stars burn and neurons fire are laws of conservation. Even entropy, which appears to measure loss, is really a record of distribution, energy spreading so that nothing is wasted. Cosmologists like Sean Carroll sometimes call this the eternal equilibrium. In that far future state, the universe will not vanish. It will settle into a calm so even that no single event stands out. It will be a kind of cosmic quiet. Not darkness, not nothingness, but perfect balance. And here the language of physics begins to overlap with something almost poetic. Because balance feels familiar. It is what we recognize when motion slows, when a wave rests after breaking, when a thought concludes and another begins. The silence between notes in a song is not the end of the music. It is part of the rhythm that allows the next note to exist. In that way, perhaps the universe is music written in the language of mathematics, each vibration a particle, each chord a galaxy, the melody unending. What we call endings are simply rests, pauses where the pattern shifts before rising again. Quantum field theory provides a literal version of this metaphor. Fields vibrate with quantized energies. Even at absolute zero, those vibrations do not stop. The 0-point energy remains. That faint hum is the lowest possible whisper of existence, the reminder that the universe never truly reaches silence. Physicists have tried to measure this hum. It shows up in the Casimir effect, a subtle force between uncharged metal plates caused by fluctuations in the vacuum itself. It shows that even in what we call empty space, something moves, something persists. The Japanese physicist Masahiro Hotta once proposed that this vacuum energy might even be tapped through quantum teleportation protocols, a theoretical way of extracting usable work from the emptiness. Whether or not that proves feasible, the idea itself is telling. Our concept of nothing continues to shrink the closer we look. The same pattern holds for the human mind. Neuroscientists studying consciousness find that awareness is not a static thing but a process. Oscillations of neural activity, rhythms that coordinate perception, memory, and thought. When those rhythms cease, consciousness as we know it changes, but the underlying matter, the information encoded in connections and molecules, does not vanish. It disperses into the world that created it. From a purely physical standpoint, that dispersal is continuation. Every atom that composes a thought will someday join the soil, the air, the stars. The network of information we call the self is temporary, but the medium that carries it is everlasting. In this sense, the great cycle of cosmology and the quiet cycle of a single life are reflections of the same law. The end of existence is not a doorway out of being, but a transformation within it. Physicists like Julian Barber have gone further, suggesting that time itself might be an illusion, that the universe is a collection of nows, each a complete configuration of everything. Motion, memory, and history are ways our brains link these moments into continuity. From that perspective, existence has no start and no finish. All moments simply are. Barber calls this timeless landscape Platonia. Within it, the idea of an ending makes no sense. What changes is the viewpoint, the path through the configurations. The end of existence becomes the end of a particular perspective, not the end of reality. Even in popular physics, echoes of this appear. Einstein wrote to a friend after the death of a colleague, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." He meant that space-time, as described by relativity, already contains every event, the whole history of the universe laid out like a four-dimensional tapestry. If that tapestry exists as a single whole, then no thread can truly be removed. The pattern of your existence is woven into it permanently. This realization does not erase the emotional meaning of change or loss. Rather, it frames them within a larger continuity. The universe does not stop when one form fades. It carries the imprint forward, encoded in fields, in radiation, in the quiet structure of space itself. In quantum mechanics, there is a concept known as unitarity, the principle that the total probability of all outcomes always equals 1. It ensures that quantum evolution preserves information. What changes are the relationships among states, not the sum total of existence. Unitarity is mathematics' way of saying that the universe keeps perfect books. To physicists who ponder the ultimate fate of reality, unitarity is both a comfort and a challenge. It means that no matter how extreme the transformation, even at the singularity of a black hole or the heat death of the cosmos, the grand accounting remains balanced. And perhaps that is the quiet truth behind the fear some scientists feel when they speak of the end of existence, that the universe might be more permanent than they expected, and that the self, being part of that universe, might also belong to a continuity that cannot be undone. In laboratories and observatories around the world, instruments continue to listen for whispers of this continuity. The laser interferometer, gravitational wave observatory, hears ripples in space-time from collisions of black holes billions of light-years away. The James Webb Space Telescope peers back toward the earliest galaxies, catching light that began its journey almost 14 billion years ago. Each observation adds another thread to the pattern, confirming again and again that existence extends beyond our immediate horizon, and in that recognition, many physicists find not fear but a kind of peace. They see that the laws they uncover are not arbitrary. They describe a universe that conserves, recycles, renews. Energy does not end, it transforms. Information does not vanish, it reappears in new forms. Patterns dissolve only to make room for others. You can imagine this as the breath of the cosmos, an expansion, a pause, a contraction, a new beginning. The rhythm continues, and within it every observer, every consciousness plays a part. So, as we return to the phrase that began this reflection, the end of existence, it becomes less a statement of finality and more an invitation to see beyond limits. The end is a perspective, a horizon drawn by the observer. Beyond it, the field goes on. In quantum theory, there is no boundary between observer and observed, only interaction. Each act of seeing, each moment of awareness, is a link in the chain that keeps the universe coherent. As long as there is observation, there is existence, and as long as existence continues, there will be observers. This, perhaps, is what truly fascinates and unsettles quantum scientists. That their measurements, their equations, their search for an end, always circle back to themselves, to the fact that the universe seems unable to exclude awareness from its description. It means that the cosmos is not merely out there, it is also in here. Every particle that drifts through space participates in the same physical laws that animate a human thought. Every field that ripples through the vacuum is kin to the field of perception that recognizes it. And in that unity, the phrase, "the end of existence," loses its sting. There is only transformation, recurrence, and the unbroken continuity of the whole. When you pause to feel this, perhaps late at night, the idea of an end begins to soften into something vast and quiet. The stars above are not separate from you. They are the history of your own atoms shining back across time. The light that leaves them tonight will travel for eons, but it will never be lost. It will scatter, interact, change frequency, but somewhere in the fabric of space, it will continue to exist. And so will everything else. The universe keeps its records. Existence, it seems, never truly ends. The more researchers learn about the fabric of the cosmos, the more it seems to behave like a vast, self-recording system. Every interaction leaves a trace. When a photon bounces off an atom, when a gravitational wave passes through a cloud of gas, when two particles exchange information, a pattern is written. Over cosmic time, those patterns accumulate, woven together into the history of the universe. Physicist Seth Lloyd once estimated that the observable universe has performed roughly 1,090 logical operations since the Big Bang. Each interaction, a scattering, an absorption, a decay, is a bit of computation. From that perspective, the universe itself is a quantum computer, running the algorithm of its own evolution. And, like any computation governed by unitarity, its information is conserved. The output is never erased. It is transformed, entangled, redistributed. That principle has practical consequences. In the last 2 decades, experiments in quantum information have begun to probe how nature guards her data. Quantum error correction, the same principle that keeps information stable inside a quantum computer, also appears to describe how space itself stays coherent. Theorists such as Juan Maldacena and Leonard Susskind discovered that the mathematics of entanglement can reproduce the geometry of spacetime, the famous EPR conjecture, in which wormholes and entanglement are 2 descriptions of the same connection. If they are right, spacetime is not a background at all. It is the geometry of information. The where of the universe is written in the pattern of its correlations. In that light, existence does not end because information cannot be uncorrelated into nothing. The web only shifts shape. When we look to the largest scales, the same logic reappears. The cosmic microwave background, that faint afterglow left from the first 380,000 years after the Big Bang, is a perfect memory of the early universe. Tiny variations in its temperature, 1 part in $100,000, record the primordial quantum fluctuations that seeded every galaxy. Those patterns are still visible today, stretched across the sky like a fossilized echo. At the opposite extreme, inside the heart of a black hole, the physics is still uncertain. But holographic theories suggest that the surface area of a black hole, not its volume, measures the information it contains. The so-called holographic principle, proposed by 't Hooft and Susskind, implies that all the information about a region of space can be encoded on its boundary. If this is true, then the entire universe could be described by information inscribed on a distant cosmic horizon. Once again, no data lost, only rewritten on a new surface. This notion that the universe keeps its own record resonates with the intuition many scientists feel when they study conservation laws. Nothing disappears. The total energy of the cosmos remains constant. The total momentum is balanced. The total charge is neutral. Reality preserves its bookkeeping with a precision no human institution could match. Perhaps that is why the idea of a final end feels so foreign to physics. An end would violate the symmetry that every experiment affirms. At the same time, the deeper these symmetries run, the more they resemble the principles of life itself. In biology, too, information is never static. DNA is a language of 4 letters that writes, copies, mutates, and evolves. When an organism dies, its molecules disperse, but the genetic information it carried persists in relatives, in offspring, in the wider ecosystem. The carbon of its body joins new chemical networks. Its energy returns to the cycle of metabolism and sunlight. Life, in this sense, is a localized decrease in entropy, a small region of order maintained by exporting disorder to the surroundings. The Earth receives low entropy energy from the Sun and radiates high entropy heat into space, sustaining a steady flow that powers everything from photosynthesis to thought. As long as that flow continues, the planet remains a cradle of complexity. Even on planetary scales, this pattern repeats. Stars form from collapsing gas, ignite fusion, enrich space with heavy elements, and give rise to new generations of stars. Galaxies merge, feed black holes, and fling material back into intergalactic space, from which more structures emerge. Every process feeds the next. The universe is recursive, self-referential, eternally inventive. Some cosmologists have begun to think of this not just as a metaphor, but as a principle. Cosmic natural selection. Lee Smolin proposed that universes might reproduce through black holes, each new universe inheriting physical constants slightly different from its parent. If such a mechanism exists, then the cosmos is literally an evolutionary system, favoring universes that maximize the formation of black holes, and, incidentally, of the heavy elements and stable stars needed for life. In that picture, even universes evolve. Whether or not Smolin's conjecture is correct, it captures an important theme: that existence tends toward diversity, complexity, and continuation. The equations allow these tendencies. Observation confirms them. For the scientists who dedicate their lives to these questions, there is both humility and wonder in realizing how persistent the universe is. It resists absolute stillness. Energy always finds new forms. Information always finds new arrangements. The cosmos is a story that rewrites itself forever. When they stand at telescopes or particle accelerators, these scientists are not just gathering data. They are participating in the act of the universe examining its own pattern. Every measurement is a feedback loop, a small instance of Wheeler's self-excited circuit in action. In that sense, awareness, whether human or otherwise, is the cosmos looking into a mirror. What then would it mean for that mirror to break? If all awareness vanished, if every observer were gone, would existence still exist? Quantum theory hints that this question may be meaningless. Observation and existence are two sides of the same process. The act of measurement does not create reality from nothing. It articulates reality's possibilities. Without articulation, the possibilities remain, waiting. The philosopher Thomas Nagel once wrote that consciousness gives the universe its inside. Physics describes the outside, the relationships, the behavior, the measurable. Consciousness is what it feels like for the universe to experience those relationships from within. If so, the interior and exterior are inseparable. The end of existence, then, would require the end of both sides of that coin. An impossibility, because each defines the other. Without form, there is no experience, and without experience, there is no recognition of form. Reality is the dialogue between them. This insight may not comfort everyone, but it provides a frame for awe. It suggests that when we study the cosmos, we are not strangers in a foreign land. We are local expressions of its own capacity to understand. The atoms in our eyes were once plasma in ancient stars. The neural signals that produce curiosity are guided by the same electromagnetic forces that govern galaxies. The drive to know is itself a law of physics written in the language of biology. Every discovery, every equation, every quiet night of observation adds to the story of a universe discovering itself. And so, the end of existence remains elusive, not because it is distant, but because existence does not possess that kind of boundary. Perhaps the best we can do is describe transitions, from order to disorder, from hot to cold, from complexity to simplicity, and back again. Each transition is both an ending and a beginning, the hinge of an unending rhythm. When you think of it this way, the entire history of the universe becomes a single, continuous gesture, the expansion of potential into reality, the relaxation of energy back into equilibrium, and the rise of new potential once more. An unbroken circuit. Even language struggles to keep pace with that idea. We speak of was and will be, but the universe seems to prefer is. It is now, everywhere, always. From the quantum fluctuations beneath your fingertips to the cosmic background radiation at the edge of observation, the same present unfolds. The future will not be a void. It will be a different arrangement of the same substance, still breathing, still alive in its own mathematical way. And that, perhaps, is the quiet truth hidden in the equations that both terrify and comfort the scientists who study them. That existence may not know how to stop. Among the deepest puzzles facing theoretical physics today is the question of why the laws of nature appear so exquisitely tuned for complexity. A slight difference in the strength of the strong nuclear force, the electric charge of the electron, or the rate of cosmic expansion, and the universe would be barren. This precision unsettles many researchers. It hints either at a multiverse where countless universes exist with varying constants, or at some underlying principle we do not yet grasp. The fine-tuning problem, as it is called, is sometimes framed as evidence of selection. Not in a teleological sense, but as a statistical inevitability. If countless universes arise, only those with the right parameters for stability will give rise to observers capable of asking the is question. This anthropic reasoning, though controversial, ties consciousness again to the fabric of reality. The laws that permit awareness are, by definition, the ones that awareness can perceive. It was Brandon Carter in 1973 who first articulated the anthropic principle. Since then, it has grown from a philosophical observation into a constraint used in cosmological modeling. Physicists like Andrei Lund and Alexander Vilenkin applied it to inflationary cosmology, suggesting that eternal inflation spawns regions of space with different vacuum states, each potentially a separate universe with its own constants. In this multiverse landscape, our existence is not improbable. It is necessary somewhere. Still, the implication is staggering. It means the cosmos might be infinite in scope, and that endings, even local ones, are mere transitions within an endless sea of variation. Quantum cosmology approaches this same question through the lens of the wave function of the universe. In the Hartley-Hawking model, proposed by James Hartle and Stephen Hawking in the 1980s, the universe has no boundary in imaginary time. The Big Bang is not a singular beginning but a smooth curve, time turning into space at the earliest moment. If that geometry holds, then the universe does not require an origin or an end. It simply is, finite yet unbounded, like the surface of a sphere. To picture it, imagine the globe of Earth. You can travel north until you reach the pole, but there is no edge. Beyond the pole, you move south again. The path continues without a border. So, too, in the Hartle-Hawking model, the cosmos wraps around itself in higher dimensional space-time. This idea, though mathematically dense, resonates with an ancient intuition that the universe might be a self-contained whole with no outside, no beyond, no ultimate boundary. And if the cosmos has no boundary, then neither does existence. Our experience of beginnings and endings, of birth and death, are local phenomena, defined by perspective within a continuum that knows only transformation. This theme repeats across disciplines. In quantum field theory, particles are excitations of underlying fields. In biology, organisms are expressions of the same chemistry cycling through ecosystems. In geology, continents drift, erode, and reassemble. In stellar evolution, matter collapses, explodes, and reforms. The same patterns echo from quarks to quasars. For quantum scientists, the recognition of these self-similar patterns evokes a strange mixture of awe and discomfort. Awe, because it reveals a unity that transcends scale. Discomfort, because it undermines the cherished assumption that separateness is fundamental. The more deeply they look, the less isolated anything appears. Consider the experiments in quantum entanglement conducted by Alain Aspect, Anton Zeilinger, and John Clauser, work that earned them the Nobel Prize in 2022. Their measurements closed the remaining loopholes in Bell's inequalities, demonstrating that entangled particles behave as a single system even when separated by vast distances. Local realism, the idea that physical properties exist independently of observation, could not account for the data. The universe, it seemed, was non-local at its core. This non-locality forces a re-evaluation of what it means for something to end. If all parts of the system are correlated, then the disappearance of one part is simply the redistribution of relationships across the whole. Nothing vanishes, connections shift. In that sense, the universe functions more like a symphony than a machine. Each note has meaning only within the harmony. When a note fades, its resonance lingers in the chords that follow. The end of a melody is not silence, but the preparation of another. This concept surfaces again in quantum decoherence, the process by which quantum systems interact with their environment and lose their coherent superpositions. Decoherence explains why we observe classical outcomes instead of quantum probabilities. It is the mechanism by which the world appears solid. But it is not destruction. The information contained in the superposition is not lost. It becomes entangled with the environment. The wave function still evolves unitarily. Once again, the universe keeps its record. When you step back from the mathematics and think about what that means, it suggests a remarkable continuity. Even at the smallest scale, where events flicker faster than any instrument can track, nothing truly ends. The story is written in correlations, and correlations have no final chapter. This persistence extends to light itself. Photons travel across billions of years, red-shifting as the universe expands, but never ceasing. When they encounter matter, they may be absorbed, raising an electron to a higher energy level. Yet the information they carried is preserved in the changed state of the system. Light, in this way, is the perfect symbol of unbroken existence. A messenger that never entirely disappears, only transfers its identity. When astronomers detect the faint afterglow of the cosmic microwave background, they are catching photons that have been traveling since the universe became transparent. Those particles of light have crossed nearly the entire age of time. They are the oldest witnesses we can still receive, and even after being absorbed by a detector, their imprint continues in data, in knowledge, in understanding. So even when we say the light has reached us, it is not an end. It is another transformation in an unending relay. There is another way to see this continuity, one drawn from mathematics itself. In topology, a sphere and a cube can be continuously deformed into each other without cutting or gluing. They are distinct in appearance but identical in essential connectivity. Likewise, the universe may undergo transformations that seem drastic from within, but preserve its underlying topology, its connectivity of information. The ultimate end, then, would require a tear in that connectivity, a violation of unitarity, a true break in the web. So far, no law of physics allows such a break, even at the Planck scale, where quantum gravity reigns and space-time itself may fluctuate. Theorists expect continuity of information to hold. The form of that continuity may be beyond our imagination, but its presence seems unavoidable. And so, quantum scientists continue to explore, part a curiosity, part existential courage. They design experiments to probe ever finer distinctions, the lifetime of virtual particles, the oscillations of neutrinos, the faint gravitational waves from merging neutron stars. Each discovery adds another verse to the same ongoing poem of reality, a poem without a final line. When you read the papers and the technical language, you see numbers, probabilities, symmetries. But beneath the calculations lies a quiet wonder that many physicists admit privately, that the universe's refusal to end might be its most profound property. This recognition has philosophical consequences. If existence is continuous, then meaning cannot depend on permanence of form. Meaning must reside in participation, in the act of being part of the ongoing transformation. That realization changes the emotional texture of the question. The fear that the cosmos will end, or that awareness itself might vanish, gives way to curiosity about the larger pattern in which change occurs. It becomes less about loss and more about rhythm. Even the act of thinking this thought, of imagining the far future and the persistence of laws, is itself a continuation of the universe's unfolding intelligence. Through every observer, the cosmos reflects on its own endurance. To the scientists who dare to map this endlessness, the work is both rigorous and intimate. They know their equations may one day be replaced, their theories refined, their lives brief. Yet they also know that each insight, once expressed, joins the collective memory of humanity, a record that may outlast stars. In that sense, they have already touched eternity, not through immortality, but through connection. Their work becomes a part of the cosmic archive, the unbroken ledger of existence that the universe seems intent on keeping. And if, someday, another civilization looks up at their own sky and wonders how it all began and how it will end, the same continuity will greet them. They will find the same laws, the same constants, perhaps even the same awe. For the universe, in all its infinite variety, tells one story: that existence persists, that endings are perspectives, that every transformation is a continuation seen from a different point of view. If you trace the story of the universe back to its earliest moment, every point of space was once compressed into an unimaginably hot and dense state. But that point was not inside anything. It was space itself. There was no edge, no surrounding void, only the newborn expansion of energy and time. Physicists still debate what, if anything, came before that expansion. In quantum cosmology, the word before may not even apply. Time could be an emergent property, born with the universe itself. Hawking once compared it to the surface of the Earth. You can travel south until you reach the South Pole, but asking what lies further south makes no sense. The Big Bang is that pole, a coordinate, not a border. The mathematics of the early universe tells us that even then, fluctuations already rippled through the fabric of energy. Those tiny irregularities became the seeds of galaxies. Every planet, every living thing, every consciousness owes its existence to those primordial tremors. From the very start, the universe contained the potential for observers who would later look back and measure it. This reflexive quality, the cosmos giving rise to beings who can understand the cosmos, is what continues to fascinate quantum scientists. It suggests that the structure of reality permits self-reference. Wheeler's participatory universe again. The observer and the observed co-creating the narrative of being. It is not mysticism to recognize this. It is an acknowledgement of symmetry. The same equations that govern the behavior of subatomic particles also govern the light that carries images to the retina, the impulses that travel through neurons, the synaptic patterns that form a thought. The human mind is not separate from the universe it studies. It is one of its natural outcomes. That realization blurs the line between physics and philosophy. When consciousness reflects on existence, the universe is, in a sense, reflecting on itself. Through us, through any form capable of awareness, the cosmos becomes self-aware. In the 20th century, physicist Eugene Wigner speculated about the consciousness of the observer as a necessary component of measurement. Although most physicists now frame the measurement problem without invoking mind directly, the role of observation remains central. At some level, reality seems incomplete until it interacts, until probabilities give way to outcomes. This inherent relational nature is what quantum theory captures so elegantly, and what makes the idea of an end so elusive. For even if every particle decayed, every star cooled, and every structure dissolved, the relationships, the laws, the potential for pattern would remain. They are not material in the ordinary sense. They are the grammar of being itself. To many physicists, this grammar is expressed in mathematics. To others, it might as well be called symmetry, information, or order. But whatever the name, it persists. Theoretical physicist Frank Wilczek describes this persistence as the persistence of pattern. He writes that the universe is a conversation among patterns that never fully ends. Each one echoes, combines, and recombines into new forms. The continuity of these patterns is what gives rise to the physical constants and forces we observe. When you see light refracted through a droplet into a rainbow, that color gradient is a local expression of universal order. The equations of electromagnetism and geometry manifesting briefly in water and sunlight. When you listen to music, harmonics and resonance mirror the physics of waves. In both, the universe reveals its tendency toward structure. At larger scales, galaxies cluster in filaments that form a web-like structure across the cosmos. Astronomers mapping this cosmic web with surveys like the Sloan Digital Sky Survey have found that the distribution of matter resembles neural networks. Filaments connected by nodes, voids separating them. The pattern of the universe and the pattern of the human brain, though vastly different in scale, follow similar mathematical rules. Such parallels remind us that existence might be a single phenomenon appearing in countless guises, and when those guises change, we interpret it as an ending. But the field that generates them continues, ever fertile, ever creative. There is an elegance in this continuity. It means that nothing is wasted, Every collapse feeds the next expansion. Every quiet moment between stars is the cradle of a future constellation. Even now, deep within molecular clouds, new suns are forming. They will ignite, surround themselves with planets, and perhaps give rise to life that wonders, as we do, about beginnings and endings. Long after our civilization is gone, those lights will still shine, carrying forward the same physical laws, the same potential for awareness. For quantum scientists, the knowledge that the universe regenerates endlessly can be both humbling and strangely comforting. It means that our brief existence is not an exception but part of the continuum. The atoms that compose us have traveled through generations of stars. They have been part of countless forms before and will become countless forms again. And even beyond matter, the information carried in every interaction, the record of what has been, contributes to the ongoing story. Entropy disperses, but it does not annihilate. Information remains encoded in the correlations that link one moment to another. When cosmologists simulate the far future, they describe epochs of unimaginable duration. Yet their equations never find an absolute termination. There is always a residual field, a background, a possibility. Perhaps that is the simplest definition of existence, that which can always become something else. As the narrative of science unfolds, each generation of researchers inherits the work of the last, refines it, and adds a little more. Their collective effort mirrors the universe itself, an unending process of iteration and renewal. The same pattern runs through history, through life, through every heartbeat. There is motion, stillness, motion again. The end is never an end, it is a change of rhythm. In the cosmic sense, existence appears as a single, continuous gesture. The gesture may vary in scale and tempo, but its essence remains: transformation without loss, variation without void. It may be that this is what existence means, not a static state, not an isolated moment, but a verb, an ongoing act. To exist is to participate in the perpetual unfolding of form into form. Even if one day the stars fade from the sky and the last photons stretch into darkness, the fabric that carried them will remain. Its equations will still hold. Its symmetry will still define what is possible. The stage will not collapse. It will rest, waiting for another act. And somewhere, in that calm equilibrium, the potential for awareness, however it may manifest, will persist as it always has. The scientists who explore these mysteries know that they are finite, that their lifetimes are brief against the measure of the universe. Yet their curiosity connects them to something timeless. Every observation, every experiment, every equation is a way of joining the ongoing dialogue of existence. Through them, the universe continues to learn about itself. To recognize that continuity is to see that nothing truly stands alone. The light of one star illuminates another. The understanding of one mind sparks countless others. Even as individual forms pass, the exchange continues. From the fusion of atoms to the emergence of thought, from the expansion of galaxies to the reflection in a quiet human gaze, the same principle endures: transformation without extinction. Perhaps that is what the physicists mean when they speak, half in jest and half in awe, of being terrified by the end of existence. Not terrified of nothingness, but of the realization that there may be no final boundary, that the universe and consciousness within it are parts of a process that cannot stop. The terror and the beauty are one. They arise from the same infinite continuity that began with a spark of light and will continue long after that light has changed form. The cosmos carries on, patient, unhurried, writing and rewriting itself in the language of physics, of pattern, of awareness. And somewhere within that unbroken story, every one of us plays our brief and luminous part. When cosmologists simulate the far future of the universe, they use the same equations that describe its earliest moments. Einstein's field equations, quantum field theory, and the laws of thermodynamics together paint a picture of endless transformation. Even when the equations predict that stars will burn out and galaxies will drift apart, they also imply that the underlying fabric of reality, space-time itself, will endure. At first, this endurance seems almost paradoxical. If all the visible matter and radiation fade away, what is left to call a universe? Yet the field remains, and with it the potential for new structures, new fluctuations, new beginnings. Astrophysicists divide the far future into eras, each defined by the dominant form of matter and energy. We are living in what they call the stelliferous era, when stars illuminate galaxies and fuel the chemistry of life. This era will last for trillions of years, far longer than the current age of the universe. As long as hydrogen remains in the cores of stars, the cosmos will shine. But hydrogen is finite. Eventually, fusion will exhaust itself, and the bright lights will dim. Planets will freeze, stars will shrink into white dwarfs, and galaxies will grow dark. Yet, even in that darkness, something continues. White dwarfs will crystallize into dense spheres of carbon and oxygen, cooling for quadrillions of years until they become black dwarfs. Still there, silent, enduring. Occasionally, two may collide, briefly reigniting nuclear fusion and releasing a final flash of light. Even after the visible universe fades, the physics of possibility remains. On timescales beyond comprehension, even protons may decay, though experiments have yet to observe it. If proton decay is real, matter itself will gradually transform into radiation. That radiation will spread, thinning as space continues to expand. At this stage, black holes dominate. They swallow stars, gas, and even each other, merging into larger and larger entities. And then, through Hawking radiation, they too begin to evaporate, emitting a faint stream of particles. A supermassive black hole may take 10 to 100 years to vanish, but vanish it will. When the last black hole evaporates, the universe will enter the dark era, a state of near-complete equilibrium. Matter as we know it will be gone. The cosmos will consist of low-energy photons, neutrinos, and the thin whisper of quantum fields. But even this is not nothing. At that point, quantum fluctuations will still stir the vacuum. Tiny virtual particles will blink into and out of existence, maintaining the restless hum of the quantum field. These fluctuations, though fleeting, ensure that the universe can never reach absolute zero entropy. There is always motion, however faint. Physicist Lawrence Krauss once described this future as a sea of eternal light. It may be faint, stretched by the expansion of space until its wavelength spans entire galaxies, but it will still exist, the last echo of creation. In that nearly timeless state, new possibilities arise. Quantum tunneling could, in principle, produce new inflationary bubbles, regions where a fluctuation triggers another Big Bang, birthing a new universe with its own space-time and constants. If such events occur, the multiverse continues, an infinite recursion of creation from decay. The idea is speculative but grounded in known principles. Inflation itself was likely triggered by such a fluctuation in the early vacuum. If it happened once, physics suggests it could happen again and again without end. In that view, the cosmos is like an eternal forest. Stars and galaxies are the trees that grow, die, and release seeds, quantum fluctuations that give rise to new universes. The forest never empties. It regenerates forever. For quantum scientists, this picture erases the boundary between origin and destiny. The end of one epoch becomes the prelude to the next. Existence folds back upon itself in a cycle that requires no external cause. At this scale, the human mind struggles to hold the image. We are accustomed to narratives with beginnings, middles, and ends. But the cosmos, according to its own mathematics, seems to prefer continuity, a story without a final page. This continuity shows up even in laboratory physics. In 2019, researchers at the University of Chicago measured correlations between entangled photons that persisted even after they traveled separate paths. When one photon's properties were measured, the information about its twin was instantly known, not transmitted faster than light, but revealed as part of a single unified system. That unity is what modern physics keeps uncovering. From this perspective, the end of existence is not a physical event, but a linguistic one, a boundary created by limited perception. Every theory that once predicted an absolute void has, under closer inspection, revealed a deeper layer of persistence. The vacuum was once thought to be empty. Now it is known to be full of fields. The universe was once thought to be eternal, then finite. Now possibly infinite again through cycles or branching. Our understanding evolves, but the pattern remains. Continuity beneath apparent cessation. For scientists like Penrose and Tegmark, this realization is not merely intellectual. It changes how one perceives existence itself. When Penrose speaks of his conformal cycles, or Tegmark of his mathematical universe, both point toward a cosmos that refuses to vanish. Even if our specific forms are temporary, the structure that allows form persists. In the end, if there is an end, the universe may find itself indistinguishable from its beginning, smooth, uniform, timeless. And from that simplicity, another burst of complexity may arise, an infinite respiration, beyond time, beyond measure. Seen from within, such vastness can seem cold. But the deeper one studies it, the more it reveals an unexpected grace. That existence, in all its complexity and impermanence, participates in something that endures. Every scientist who adds a line to an equation, every observer who measures a star, every person who looks up at the night sky contributes to that continuity. We are part of the same process, made of the same matter, governed by the same laws. When we think about the end, what we really confront is the limit of our current form, not the limit of reality itself. Physics teaches that transformation is fundamental. It is the simplest and most universal truth the universe offers. The hydrogen in stars becomes helium. Helium becomes carbon, oxygen, and iron. Those elements form planets, oceans, living cells, and thought. Thought creates understanding, and understanding shapes the future. The circle closes only to open again. When the universe grows cold and silent, it will still carry the memory of its own patterns, the record of everything that has ever been. And if, from that record, another universe blooms, the pattern continues. The end of existence, as quantum scientists see it, may not be a wall at all, but a reflection, the point at which existence turns back on itself, endlessly renewed. When physicists talk about the rebirth of universes from quantum fields, they are not reaching for metaphor. They are following the mathematics to its logical edge. Inflation theory itself was born from such reasoning. In the 1980s, Alan Guth and Andre Linde realized that a scalar field with high potential energy could drive exponential expansion, a process that smooths irregularities and seeds the cosmos with structure. In their equations, inflation need not stop everywhere at once. Pockets of space can finish inflating while others continue, creating bubbles of new universes adrift in a still expanding background. Each bubble cools, forms its own physical constants, and unfolds its own history. In one, the strength of gravity may differ slightly. In another, the ratio of dark energy to matter may shift. Most of these regions would be sterile, unable to form stable atoms or galaxies. But some, like ours, settle into balance. The multiverse, in this picture, is a vast landscape of possibilities. It never ends because its mechanism of creation is built into its nature. To many researchers, this idea is both elegant and disquieting. It means there is no singular beginning and no final end, only perpetual variation. The equations that describe it are the same ones that describe quantum fluctuations in a laboratory vacuum. The same physics that allows a particle to blink into existence also allows entire universes to bloom. Even if these ideas remain beyond direct observation, they remind us of something fundamental. The laws of physics appear to be self-consistent, self-generating, and endlessly fertile. From simplicity arises complexity, and from complexity, simplicity again. In 2017, cosmologists working with the Planck satellite published the most detailed map yet of the cosmic microwave background. The map showed minute variations in temperature. Relics of quantum fluctuations stretched across the sky. Those fluctuations are the fingerprints of the universe's own birth. They tell us that randomness and order are intertwined, that the seeds of everything we see were once quantum tremors smaller than an atom. Such results close a circle between the smallest and the largest scales. They confirm that the same quantum behavior governing subatomic particles shaped the destiny of galaxies. The very laws that create uncertainty at the micro level also create structure at the macro. To a quantum scientist, this unity is the most haunting part of all. It implies that the universe is not merely large, it is coherent. Its pieces are not fragments but expressions of a single set of rules. When those rules are written in mathematics, they show a tendency toward balance. Symmetry and conservation recur everywhere. Noether's theorem, one of the most beautiful results in physics, states that every symmetry corresponds to a conservation law. Time symmetry yields energy conservation. Spatial symmetry yields momentum conservation. The universe protects its quantities the way a poet protects rhythm. If those symmetries were ever truly broken, existence itself would unravel. But every experiment so far, from particle colliders to cosmic observations, confirms their steadfastness. Reality maintains its accounting with exquisite precision. This constancy suggests that the end of existence, if it exists at all, could only come from a violation of these symmetries, something outside known physics. And yet, even speculative theories of quantum gravity, from string theory to loop models, preserve unitarity and conservation. The continuity seems absolute. For many scientists, this persistence is the closest thing the universe has to immortality. not immortality of form or mind, but of law, the endurance of the framework that makes anything possible. In recent years, researchers exploring the holographic principle have found that information at the edge of a region of space fully describes its interior. This discovery grew from studies of black hole thermodynamics, where entropy, a measure of information, scales with surface area, not volume. If applied to the cosmos as a whole, it implies that every event inside the universe is mirrored on its boundary. In some sense, existence is already encoded in its totality. That means the universe could end many times within, through the collapse of stars or civilizations, yet remain whole. Its information is always preserved somewhere, woven into the larger pattern. For human observers, this realization brings a peculiar mixture of smallness and connection. Small, because our lifespan and scale are minute compared to cosmic time. Connected, because every atom and every photon is part of the same unbroken network. When cosmologists look toward the horizon of the observable universe, they see light that has traveled for nearly 14 billion years. That light carries the record of the earliest structures. Beyond it, space continues, regions we will never observe, yet which obey the same laws. To imagine that endlessness is to encounter a kind of silence, not emptiness, but completion. Every possibility already contained, every equation already balanced. And yet, within that balance, novelty continues to arise. Quantum fluctuations do not repeat exactly, they generate variation. Each variation is a new pattern, a new experiment in form. Perhaps that is the universe's most enduring trait, its curiosity. It explores every configuration of its laws, every symmetry and asymmetry, until all possibilities are expressed. For scientists who spend their lives tracing these patterns, the work becomes a dialogue with that curiosity. They are not outside it, they are part of it, agents through which the universe refines its understanding. From the first physicist who measured the fall of an apple to the teams operating particle accelerators today, every question extends the self-knowledge of the cosmos. Each observation reduces uncertainty somewhere, but increases it elsewhere, a perpetual balancing act. And so, the scientific enterprise mirrors the cosmos itself. Expansion, reflection, correction, renewal. It never truly finishes. Even if one day no human mind remains, the potential for awareness embedded in the structure of matter endures. Given time, and the universe has time in abundance, the same laws could generate new complexity, new observers, new questions. Nothing in physics forbids it. The constants that allowed consciousness once could allow it again. This is what makes quantum scientists terrified by the end of existence. Not a fear of nothingness, but awe at the realization that true finality might be impossible. The equations refuse to stop. They predict transition, decay, rebirth, but not erasure. When we step outside under the night sky and see starlight that began its journey before our species existed, we are witnessing that refusal firsthand. The light persists. So does the space it crosses, the laws that guide it, and the minds capable of wondering at it. From the smallest oscillation of a particle to the grandest sweep of galaxies, existence demonstrates one lesson again and again. Continuity is stronger than conclusion. The cosmos moves forward, gathering every transformation into the unbroken ledger of being, never closing the book, never writing the end. In recent decades, information theory has become the quiet thread weaving through almost every branch of physics. What began as a mathematical tool for telecommunications has turned into a universal language describing how the universe organizes itself. The Austrian physicist Anton Zeilinger, who helped to pioneer quantum teleportation, put it plainly. What we call reality is, in the final analysis, information. In classical physics, information was an afterthought, a way to describe the arrangement of matter. But in quantum physics, information and reality are inseparable. A quantum state is a catalog of possibilities. The act of measurement extracts one bit of information, and that bit becomes part of the world's story. Every interaction is a transaction of information, recorded in the correlations among particles. When Landauer declared that information is physical, he meant that even the smallest bit, a 1 or a 0, requires energy to store, process, or erase. This insight, though simple, had profound consequences. It meant that the universe's informational content is bound to its thermodynamic state. Entropy is not merely disorder, it is a measure of information dispersed into the environment. From this, modern physicists have begun to see the cosmos as an immense information processor. Each star, each atom, each photon participates in the computation of the universe's next state. The total information may be unimaginably vast, around 1090 bits within the observable cosmos, yet it is finite, structured, and governed by clear rules. This way of thinking connects physics to computation and, surprisingly, to consciousness. Quantum computers exploit superposition and entanglement, two of the same principles that shape the fabric of space-time. When researchers test these machines, they are also probing how information behaves at the most fundamental level. It is as if the same physics that drives the universe also underlies the logic of thought. If existence is informational at its core, then the end of existence would mean the loss of all information, an impossibility within known laws. Unitary evolution, the bedrock of quantum mechanics, forbids it. Information may change form, become inaccessible, or scatter beyond observation, but it cannot vanish. In this sense, existence is not a thing but a conversation that never stops. Physicists have begun to formalize this intuition through quantum information conservation. Black hole thermodynamics, holography, and the ADS-CFT correspondence all converge on the same point. Information is preserved even in the most extreme conditions. What falls into a black hole is encoded in the radiation it emits. What crosses a cosmic horizon remains imprinted on that boundary. The universe, then, behaves like a perfect archivist. It may compress, encrypt, or scatter its data, but the record remains. The end becomes a change in accessibility, not a deletion. Theoretical physicist Leonard Susskind once described the universe as a hologram. Every event within it can be reconstructed from information stored on its outer surface. This holographic model reconciles gravity and quantum mechanics in a way that naturally preserves unitarity. In this framework, space itself is a manifestation of entanglement. Remove the entanglement, and space dissolves, not into nothing, but into a more fundamental pattern of information. If the cosmos is holographic, its end cannot be a void. It would be a reconfiguration of the code that generates the image. The underlying data remain, waiting for new parameters to project another version of reality. Some scientists push this further. Eric Verlinde, for example, has proposed emergent gravity, the idea that gravity arises from the statistical behavior of microscopic information, much like temperature emerges from the motion of atoms. In this picture, Even space-time curvature is an expression of entropy. The universe's geometry, its motion, and its destiny all follow from information-seeking equilibrium. Equilibrium, however, does not mean stasis. On the contrary, it is a dynamic balance, the eternal adjustment of the universe's variables to preserve its total information. That balance is what we experience as time. Time is not an external flow, but the measure of change in information. This perspective reshapes the notion of beginnings and endings. If time itself is a relational property of information, then the end of time is simply the state in which no new information can be created or distinguished. The universe could approach that limit, but never cross it completely. Quantum fluctuations guarantee perpetual novelty. The same principle appears in biology. Life resists equilibrium by exchanging information and energy with its environment. Cells process data encoded in DNA. Proteins interpret those instructions, and organisms adapt through feedback loops. In doing so, life delays entropy's advance, creating local pockets of order that feed the growth of complexity. That process mirrors what the universe does on a grand scale. Stars, galaxies, and even civilizations are transient islands of low entropy, maintained by flows of information and energy. When they dissolve, their components return to the cosmic reservoir, fueling new configurations. This is why physicists speak of the arrow of time not as destruction, but as redistribution. Entropy increases, yet the total information of the system remains constant. In that constancy lies the assurance that existence does not end. It evolves. The more one studies these laws, the more one sees a quiet unity underlying them. Thermodynamics, quantum mechanics, relativity, and information theory are not separate domains. They are aspects of one framework describing how the universe maintains coherence. Even chaos, when examined closely, contains order. The equations of chaos theory reveal deterministic structure beneath apparent randomness. Fractals repeat their patterns infinitely, scaling down without limit. In those spirals and self-similar curves, one can see the same logic that governs galaxies and atoms alike, transformation that never exhausts itself. For the scientists mapping these truths, the pursuit becomes something more than analysis. It becomes participation in a grand continuity, a way of aligning thought with the rhythm of the cosmos. Their instruments and equations are extensions of curiosity, and curiosity itself is an echo of the universe's drive to explore its own possibilities. Each discovery is a conversation between the human mind and the vast pattern it inhabits. The dialogue never stops because both participants are facets of the same system. Knowledge expands, the unknown expands with it, and the equilibrium between them persists. Perhaps that is the ultimate lesson hidden in the study of the end of existence, that the universe, in every form, values balance over finality. It recycles, recalculates, and regenerates. The same laws that predict decay also ensure renewal. From a distant perspective, our moment, this brief era of luminous stars and conscious life, is a shimmering detail in a much larger pattern. But it is a necessary detail, one that completes the design of its time. Without transient forms, there would be no process. Without process, no universe. So, when quantum scientists face the idea of an ending and find themselves unsettled, it is not because they see nothing ahead. It is because they glimpse an infinity that has no boundary to rest upon, a pattern that continues forever, using every possible configuration to express itself. In that endless recombination of information, existence never truly ends. It changes syntax, rearranges meaning, writes new verses of the same universal poem, a poem whose subject is being itself. If the universe is built from information, then the next frontier in physics is to understand how that information gives rise to the geometry of space and time themselves. In recent decades, the field known as quantum gravity has become the meeting point of these questions. Researchers working in loop quantum gravity, string theory, and holography are all attempting, in different languages, to describe how spacetime emerges from deeper microscopic rules. In loop quantum gravity, space is not continuous but woven from tiny loops, each representing a quantum of area. These loops form a network called a spin foam, a constantly changing graph that defines the geometry of the universe at the Planck scale. Time is simply the way these nodes update their relationships. In that picture, the universe has no smallest particle of matter, only a smallest unit of space. Existence, again, is relational, geometry arising from connection. String theory tells the same story through vibration. Instead of points, it describes the fundamental constituents as tiny strings or membranes oscillating in multiple dimensions. Different vibrational modes correspond to different particles, just as different frequencies correspond to different notes in music. Space-time itself may be a resonance pattern of these strings, their harmonies generating gravity and other forces. Both frameworks, the loops and the strings, hint that space-time is not a static backdrop, but a dynamic fabric woven from quantum information. In holographic dualities, such as the AD-IS-CFT correspondence, space in a higher dimension emerges from the entanglement pattern of a lower dimensional field theory. When physicists map those correspondences, they find that geometry itself can be reconstructed purely from entanglement data. If you know which regions of a system are entangled with which others, you can rebuild the shape of space between them. That result, first, shown in detail by Mark van Ramstonk in 2010, was a revelation. It meant that spacetime might be an emergent property of information, that the fabric of the cosmos is literally made from relationships. Once more, the concept of an end becomes slippery. If space arises from information, its disappearance would require the annihilation of those correlations, an event for which physics has found no mechanism. Theoretical physicist Edward Witten once remarked that the search for quantum gravity is the search for the principles of consistency that the universe cannot violate. Whatever form the final theory takes, it will have to preserve that consistency. The universe, it seems, insists on coherence. From this insistence grows a profound stability. Even if local structures dissolve, stars, galaxies, or whole cosmic epochs, the underlying rules remain unchanged. The end of one domain becomes the beginning of another. The framework itself endures. At the observational frontier, new instruments continue to test these ideas. The Event Horizon Telescope, by capturing the silhouette of a black hole, confirmed predictions of general relativity that depend on spacetime geometry. Gravitational wave detectors like LIGO and Virgo measure distortions in that geometry caused by distant collisions. Every detection is a conversation between theory and observation, each confirming that the same laws hold across scales of distance and time far beyond human experience. When gravitational waves pass through Earth, they stretch and squeeze spacetime by less than the width of a proton. Yet we can detect them. That fact alone testifies to the universe's continuity. Ripples born in the final instance of dying stars still traverse billions of light years, still carry their message intact. These waves tell us that the cosmos communicates with itself. Energy becomes information. Information becomes signal. Signal becomes understanding. In that endless loop, there is no final transmission. If one asks what all this means for existence, the answer that emerges from modern physics is not mystical, but mathematical. The laws that govern reality are symmetric, unitary, and conserved. They have no built-in expiration date. The universe may change phase, cooling, expanding, cycling through eras, but it does not self-erase. From the viewpoint of thermodynamics, the drive toward equilibrium is not death. It is the universal search for balance. When a system reaches equilibrium, its microstates still fluctuate. They simply do so in harmony. The background radiation that fills space today is one example of such harmony, the residue of violent creation smoothed into near perfection, yet still alive with micro-variations. These variations, 1 part in 100,000, are what gave us everything. Had the early universe been perfectly uniform, gravity would have had nothing to pull together, and no galaxies would have formed. It was the tiny imperfections that made structure possible. Even now, small departures from balance are what sustain creativity. In that sense, the universe's imperfections are its way of ensuring that existence keeps renewing itself. Physicists sometimes express this principle through symmetry breaking. A perfect symmetry, left unbroken, would produce nothing. It is only when symmetry breaks, when one path is chosen among many, that distinct forms appear. At every scale, the same story repeats. Symmetry breaking gives birth to diversity, and diversity drives evolution. Without it, there would be no matter, no light, no complexity, no thought. So the end of existence, if we could call it that, might simply be the restoration of symmetry, a return to balance so complete that no distinctions remain. From that stillness, new asymmetries could again emerge, and the cycle would begin anew. This oscillation between order and disorder, symmetry and its breaking, seems to be the heartbeat of the universe. It can be traced from the earliest inflationary fluctuations to the chemistry of life, to the thought processes that ask these questions. Everywhere we look, the same pulse beats: creation, transformation, renewal. As the tools of science grow more precise, the boundary between physics and information, between cosmology and computation, becomes ever thinner. Quantum computers, now capable of manipulating dozens of qubits, are miniature laboratories for testing the logic of the universe. They demonstrate how coherence and entanglement generate extraordinary power from simple principles. And they remind us that reality's most fundamental resource is not matter or energy, but the ability to relate, to store, process, and exchange information. Through those relationships, the cosmos builds itself. Through understanding them, we participate in that building. The scientists who chase these frontiers often describe moments of stillness amid the complexity. Standing before data that match the equations with uncanny precision, they feel a kind of reverence. Not for mysticism, but for the clarity that mathematics reveals. A universe that is consistent, lawful, and continuous beyond imagination. They know that their own existence is fleeting, yet they also know that the patterns they uncover will outlast them. Each insight adds to the collective understanding, preserved in journals, instruments, and the digital archives that will endure as long as information can be stored. In that sense, knowledge itself becomes another form of continuity, a human echo of the cosmic conservation it describes. And so, when the discussion turns again to the end of existence, it is less a prophecy of disappearance and more a reminder of perspective. We live within transformations so vast that we mistake them for endings. But the equations, the observations, and the patterns all tell the same quiet truth. The universe continues. Its forms change, its expressions vary, but its essence, the coherent interplay of energy, information, and law, remains. It has no opposite, no outside, no true conclusion. It is the endless conversation of being with itself. When cosmologists model the ultimate future of the universe, they begin with data we can measure today: the rate of expansion, the energy density of space, the composition of matter and radiation. From these ingredients, the equations of general relativity unfold a story that spans trillions upon trillions of years. The plot is slow but certain: expansion, cooling, dilution, and yet within that slow fade, physics finds no true silence. The discovery that the expansion of the universe is accelerating, announced in 1998 through observations of distant supernovae, changed the picture forever. Instead of slowing under the pull of gravity, galaxies are moving apart faster with time, driven by a mysterious component called dark energy. Whatever dark energy is, it behaves as a property of space itself, exerting a constant pressure that counteracts gravity on the largest scales. If this acceleration continues indefinitely, distant galaxies will eventually recede faster than light can bridge the gap. Observers in the far future will see only their local cluster. Beyond it, the sky will go dark. But this cosmic isolation is not destruction. Each region of space will continue its own quiet evolution, governed by the same physics. The stage will change, not the script. In that remote epoch, the cosmological constant, the energy of the vacuum, will dominate everything. Space will expand exponentially. Matter will thin toward invisibility, and the temperature of the cosmic background will approach absolute zero. Yet the vacuum will still ripple with quantum fluctuations. Those ripples, though unimaginably faint, ensure that existence never becomes perfectly still. Some theorists, such as Paul Steinhardt and Neil Turok, have proposed alternatives to this endless acceleration. In their cyclic universe model, dark energy eventually reverses, leading to a slow contraction and a new Big Bang. The universe breathes. Expansion, contraction, rebirth. The equations that describe the cycle preserve information from one phase to the next, encoded in subtle gravitational patterns. Even more radical is Roger Penrose's conformal cyclic cosmology. He suggests that when the universe becomes smooth, uniform, and empty, when all mass has decayed and only radiation remains, it can be mathematically rescaled into a new Big Bang. The distant future of one aeon becomes the beginning of another. No new matter is created. The old universe simply transitions to a new description of time. These ideas differ in detail, but share the same heartbeat: continuity. In none of them does existence stop. Every scenario preserves the laws of physics, the conservation of information, and the unbroken coherence of reality. Meanwhile, within our present era, physicists keep probing smaller scales and earlier moments, searching for the bridge that unites quantum mechanics and gravity. They know that whatever happens at the Planck scale must obey the same rule that governs everything else: the rule of unitarity, the impossibility of absolute loss. Experiments at CERN's Large Hadron Collider have confirmed that even at energies approaching those of the early universe, the symmetries of quantum field theory hold. Future colliders and gravitational observatories will test them further. Each result refines the map of how the universe maintains its consistency. To describe these connections, some scientists use the language of networks. The universe, they say, is not a collection of objects, but a web of relationships. Nodes and links, causes and effects, correlations and flows of information. Everything that exists is a manifestation of connection. Cut the links, and reality itself unravels. Preserve them, and space, time, and matter emerge naturally. In this network view, even the void between galaxies is full of potential. Virtual particles flicker, gravitational fields stretch and relax, and quantum entanglement extends invisibly through the vacuum. The emptiness between stars is not absence. It is a medium alive with possibilities. That insight leads to a gentler way of seeing impermanence. When a star dies, its matter disperses, but its influence persists, as light, as elements, as gravitational memory. When a life ends, the matter and information that composed it return to the cosmic network, continuing in new configurations. Nothing falls out of the system. Physicist John Wheeler used to say, "The universe gives birth to observers, and observers give meaning to the universe." He imagined a participatory cosmos, in which every act of measurement completes a small piece of reality's puzzle. Even if the network of observers changes, the process continues. The act of knowing is built into the structure of the world. At this level of understanding, the word end loses its ordinary meaning. There's only change of form, change of connectivity, change of perspective. The cosmos writes, erases, and rewrites itself, but the total information, the grand sum of all relationships, remains balanced. Some researchers extend this reasoning into the domain of mathematics itself. They ask whether reality might be a specific solution within the infinite landscape of possible mathematical structures. If so, then existence is not a singular event, but a pattern selected by its own internal consistency. What appears as time and evolution within the pattern is simply the unfolding of logical relationships. Within that vast mathematical space, there is no need for an external cause or an endpoint. Consistency is both origin and destiny. When we translate that abstraction back into the language of experience, it means that the fabric of existence is self-sustaining. It requires no outside support because its rules guarantee their own persistence. The equations hold, the conservation laws endure, the flow of information continues. Every measurement we make, from the flicker of a distant quasar to the quantum noise of a laboratory laser, confirms that persistence. The same constants, the same symmetries, the same ratios recur. It is as if the universe whispers the same refrain in every experiment. I am still here. For scientists who live with these equations every day, the emotion is not pride or fear, but something quieter, respect for the resilience of nature's logic. They understand that the universe's stability is not guaranteed by chance. It is built into the mathematics of its being. And when they contemplate the unimaginable spans of time ahead, they see not a tragic fade, but a grand equilibrium. In that equilibrium, all forces balance, all energy diffuses, and yet the potential for renewal remains latent, waiting for the next fluctuation to ignite another beginning. Perhaps this is the deepest insight science has reached so far. that the universe's essence is continuity, not the repetition of sameness, but the persistence of possibility. Each transformation, however extreme, preserves the capacity for further transformation. From the first quantum tremor to the last wave of radiation, existence has never ceased becoming. And as long as the laws that make becoming possible endure, as every observation suggests they will, the story goes on. Every decade, as technology sharpens, the story grows more intricate. Astronomers map ever larger portions of the cosmic web, confirming that the distribution of galaxies follows the same statistical patterns predicted by quantum fluctuations in the early universe. Particle physicists refine their measurements of the Higgs field, searching for hints of instability that could reveal new physics. Computational cosmologists run simulations spanning billions of light years and billions of years, watching structure arise from the simplest initial conditions. In all of it, the theme persists: simple rules, endless elaboration. The equations are compact. Their consequences are infinite. This is the paradox that both delights and humbles physicists. From a few mathematical symmetries emerge the diversity of everything that can exist. Energy folds into matter, matter into life, life into awareness, and awareness into curiosity about the energy from which it came. The cycle closes with elegance that no human language can quite capture. As understanding deepens, the boundaries between disciplines fade. Quantum information theory merges with gravitational physics. Biology borrows algorithms from computation. Cosmology uses statistical mechanics once confined to chemistry. Each field reflects the others like facets of a crystal, hinting at a unity underlying all phenomena. That unity suggests that the universe may not be a collection of separate parts, but a single process, self-consistent from beginning to end. When researchers study quantum error correction, they are not only protecting fragile qubits in a laboratory. They are testing the same mathematics that may keep spacetime itself coherent. The same logical codes that preserve data in a quantum computer could describe how the universe prevents its own information from leaking away. Even the fabric of space, it seems, contains redundancy, multiple ways to store the same truth. Redundancy is resilience. From that perspective, existence resembles a conversation between order and variation, stability and creativity. It maintains balance not by staying still, but by continually exploring alternatives while never abandoning coherence. That exploration appears in everything from the orbits of electrons to the clustering of galaxies. Physicists often visualize this balance through phase space, a multidimensional landscape where every point represents a possible state of the system. As conditions change, the system traces a path through that landscape, sometimes looping, sometimes branching, but always staying within the boundaries defined by its laws. The universe's journey through its own phase space is the grandest version of this idea. It can visit countless configurations, but it cannot leave the landscape of its own consistency. Within that landscape, new forms of complexity continue to arise. Even as stars age and galaxies drift apart, gravitational interactions, quantum tunneling, and fluctuations at microscopic scales create pockets of novelty. Each pocket is a small act of creation, proof that equilibrium is never absolute. The universe breathes in constant detail. When physicists describe these processes, they often use the language of emergence, large-scale order arising from countless simple interactions. Snowflakes, sand dunes, planetary rings, neural networks, each is an emergent structure. The same mathematics describes them all. The emergence of consciousness, though not yet fully understood, fits the same pattern. A property of complex systems that process information and feedback upon themselves. In that sense, awareness is not foreign to physics. It is one of physics' natural outcomes. The particles that make a mind are the same particles that make stars. The difference lies only in arrangement and relationship. And because relationships are what give rise to space and time, the act of being aware is another expression of the universe's geometry. When a person observes a distant galaxy, light that began its journey billions of years ago completes its trajectory in that moment of sight. The observer and the observed are joined in a single event, connected across time by the constancy of physical law. The photon's existence, the retina's response, and the thought that follows are all parts of one continuum. This recognition that observation itself completes the universe's patterns is why quantum scientists often speak of beauty when they discuss equations. For them, beauty is not ornament, but coherence made visible. The same coherence governs the ultimate fate of matter and information. Even if protons decay and black holes evaporate, their decay products carry correlations that reflect their origins. Information disperses but remains present in the statistical structure of the whole. In this way, the universe resembles an endless diffusion of memory. Nothing is truly forgotten. It is encoded at finer and finer scales, waiting for new forms to read it again. This idea inspired the concept of the cosmic archive. Not a literal library, but a metaphor for the way information persists. The archive is written in radiation, in gravitational waves, in the quantum states of space itself. Every event adds a line to the record. Nothing can erase it completely. Time, then, is the process of writing and rewriting this archive. The so-called end of time would simply be the point when the writing becomes uniform, when every possible line has been inscribed. Even that state would not be nothingness. Uniformity is potential. From potential, asymmetry can arise again. A fluctuation, however small, could restart the pattern. The laws of physics contain no clause forbidding recurrence. In the equations of statistical mechanics, given infinite time, any configuration will repeat. That repetition need not be identical. It can be variation on a theme, the universe's way of composing new verses from old motifs. For the scientists who explore these ideas, the emotion is often quiet astonishment. The closer they approach to finality, the more they find continuation. Each boundary dissolves into a wider framework. Each apparent ending becomes a transformation rule. Perhaps that is the real message carried by the data and the equations alike. Existence is not a noun, but a verb, a continuous act of relation. It has no fixed edges because relations extend indefinitely. Every particle interacts, every field fluctuates, every idea links to another. Even the limits of knowledge expand as knowledge grows. When this understanding settles, the universe no longer seems like a stage where things happen and end. It feels more like a single, self-consistent event, vast, continuous, and complete. We are not outside it, nor merely within it. We are threads in its unfolding fabric, temporary configurations through which it experiences itself. In this view, the question, will existence end, loses urgency. It is replaced by another, gentler question. How will existence transform next? The answer, according to physics so far, is always the same. Through laws that endure, through patterns that reinvent themselves, through the eternal conversation of information becoming form, and form becoming information again. When physicists speak privately about what keeps them searching through endless data and difficult equations, they rarely mention certainty. They talk about curiosity. They describe a feeling that somewhere behind the complexity, there must be a single, simple principle holding everything together. Not a supernatural one, but a rule of nature so fundamental that everything else follows from it. Many think that principle is symmetry. Others call it information. But whichever term they use, it points to the same truth, a deep coherence that allows the universe to exist, evolve, and know itself. This search for coherence has shaped every major advance in science. Einstein's relativity unified space and time. Maxwell's equations unified electricity and magnetism. Quantum mechanics unified the duality of particle and wave. Each unification revealed that apparent opposites are complementary aspects of a single reality. In that context, the idea of an end to existence becomes difficult to define, because existence itself is defined by relationship. From this understanding, even death, of stars, of galaxies, of forms, is not deletion but redistribution. The iron in your blood was forged in a supernova. The calcium in your bones was born in an earlier generation of stars. When those atoms return to space, they will join other clouds, other stars, other beings. The cycle never needed a starting point. It only needs continuity. The physicist Brian Greene once wrote that the universe's story may not be a play with a beginning and an end, but a dance that loops and curls without closure. That dance can be described mathematically, yet its rhythm is something we can feel in every process around us. Growth, decay, renewal. It is the rhythm of energy becoming form and form returning to energy. Even the structure of scientific knowledge follows this pattern. A theory appears, thrives, and eventually yields to a broader framework that contains it. Newton's laws gave way to relativity, which in turn will someday be subsumed by quantum gravity. But the old theories are not discarded. They remain accurate within their domains, part of a hierarchy of understanding. Knowledge itself evolves by transformation, not extinction. In recent years, cosmologists have begun to think of the universe as a self-organizing system, akin to a vast non-equilibrium network. Complexity arises wherever energy flows and constraints interact. Stars are thermodynamic engines. Planets are gradients of energy and matter. Life is an intricate arrangement that keeps information cycling against entropy. From this point of view, existence is the perpetual balancing act between order and disorder, between information and entropy, between coherence and chaos. If that balance ever became perfect, nothing could change. But the very laws that govern the universe forbid perfect equilibrium. There is always fluctuation, always renewal. This tension between structure and randomness is what gives the universe texture. At the Planck scale, quantum foam flickers with creation and annihilation. At the galactic scale, dark matter threads form cosmic filaments that stretch for hundreds of millions of light years. Between those extremes lies everything we know, and everything that will ever know itself. Even consciousness, when viewed through this lens, is a phase of matter and information. It emerges when complexity reaches a threshold that allows feedback, memory, and anticipation. The brain does not create awareness from nothing. It channels it through patterns of electrical and chemical interaction. In that sense, awareness is another example of emergence, a pattern that the universe formed in order to perceive itself. When awareness fades, the pattern dissolves, but the matter and energy continue, rejoining the cycle. No information is lost. It changes format. The atoms of thought become the atoms of air, soil, light. Physics sees this not as consolation, but as fact. And so the narrative of science circles back to the same ancient intuition once expressed through myth and philosophy: the continuity of being. What physics adds is precision, an understanding that continuity is not mystical, but built into the conservation laws of nature. The equations leave no room for nothingness. When cosmologists model the end of time, their computers eventually output a smooth field approaching constant temperature, an ocean of low-energy photons and neutrinos. But that is not a void. It is the quiet equilibrium of a universe that has expressed all its possibilities and rests before new fluctuations begin. If new universes bud from that stillness, their parameters will differ, their histories will diverge, but the logic behind them will be the same. The continuity is not spatial or temporal, it is logical, the unbroken chain of cause, effect, and conservation. For those who study this chain, the realization brings both humility and calm. It means that the universe is not fragile. It does not need protection or intervention to persist. It persists because it cannot do otherwise. Every transformation is consistent with the last. Every ending is the rearrangement of conditions for a new beginning. Perhaps that is what the great unifying principle will ultimately be. Not a single equation carved in perfection, but a recognition that the capacity for change itself is the foundation of all being. That capacity guarantees that existence will continue to express itself in infinite forms, each governed by the same quiet rules of balance. When you look up at the night sky, the light you see left its sources long before humanity existed. Those photons travel still, their message unchanged. The cosmos endures. The same particles that once warmed the first stars now pass through your eyes, carrying the imprint of the universe's history. In that exchange, the distinction between observer and observed fades. You are part of the process that has been unfolding for billions of years. Science shows that there is no edge, no boundary, no final silence waiting beyond. There is only the ongoing interplay of law and randomness, pattern and transformation. What feels like the end is simply the place where comprehension pauses before continuing again. And in that pause, between one transformation and the next, the universe holds steady, waiting to speak once more in the language of light, gravity, and thought. If there is a final chapter to the universe's story, it will not be a sudden extinction but a long transformation that no single observer could ever fully witness. Across unimaginable timescales, structure will thin, energy will fade, and yet the equations will still balance. Even in the faintest light and lowest temperature, the symmetries of physics will remain exact. This permanence of law is perhaps the most profound discovery of science. It suggests that the universe is not arbitrary. The same constants measured on Earth appear identical in distant galaxies billions of light-years away. The ratio of an electron's charge to its mass, the speed of light, the Planck constant, all the same, everywhere, always. These numbers hold the universe together as surely as gravity binds the stars. Physicists have searched for evidence that these constants change over time. So far, they do not. Spectra from ancient quasars, gravitational wave signals from merging black holes, and the relic radiation of the Big Bang all confirm the same physics operating across cosmic history. If anything defines existence, it is this unbroken fidelity of law. From that constancy flows everything else. Because the laws are stable, stars can live for billions of years. Chemistry can build complex molecules. Biological evolution can unfold slowly enough for consciousness to arise. If those constants drifted by even a fraction, none of it would be possible. Continuity at the most fundamental level enables diversity at every higher one. As knowledge grows, our view of the cosmos has expanded from a single planet to a network of billions of galaxies. Yet, with each discovery, the pattern repeats. The same gravitational interactions that sculpt moons and tides also shape clusters of galaxies. The same quantum principles that govern electrons in an atom govern the cores of stars. Scale changes, but principle endures. Even dark energy, mysterious though it is, seems to follow a consistent rule. Measurements of the cosmic microwave background, supernovae, and baryon acoustic oscillations all suggest a constant energy density. Space expands, but the vacuum's properties stay fixed, a paradoxical stability that guarantees motion will never end. This stability does not make the universe static. It makes it creative. Given consistent laws, randomness and complexity can weave endlessly varied forms. That combination, order with freedom, defines every process we know. Physicists call this balance deterministic chaos. Systems ruled by exact equations that still produce unpredictable results because small variations amplify with time. Weather, planetary orbits, and even neural activity all display this property. The universe is lawful but not repetitive. It is bound by mathematics yet open to novelty. That openness may explain why existence never freezes into monotony. Fluctuations at the quantum level ensure that no two moments are identical. In quantum field theory, each instant is a superposition of probabilities. Observation simply samples one. The rest remain latent, forming the potential for all future events. If existence were ever to end, it would mean that potential itself had vanished, that no further states were possible. But every framework we have, from quantum mechanics to thermodynamics, forbids such a condition. There is always another possible state, another configuration consistent with the laws. The universe cannot run out of ways to be. This realization turns finality into an illusion of limited perspective. From within the brief span of a human lifetime, things begin and end, arise and fade. But the deeper one looks, the more those boundaries blur. Matter becomes energy. Energy becomes curvature. Curvature becomes the stage on which matter reappears. The loop closes with no gap. When cosmologists integrate these equations backward and forward through time, they see symmetry even across birth and death. The Big Bang is not a singular creation from nothing. It is a transition through which dense, hot conditions gave way to expansion. Its opposite, the thin, cold equilibrium of the far future, mirrors it. One extreme folds naturally into the other. This mirror structure runs through the mathematics of relativity itself. Einstein's field equations are time-symmetric. For every expanding solution, there is a contracting one. The arrow of time we perceive emerges from entropy, from the universe's movement toward greater dispersal of energy, not from any asymmetry in the laws. Reverse the boundary conditions, and the equations work equally well. So, even if the cosmos were to contract one day, physics would not break. The same symmetries would carry it through. Existence, in that sense, is self-consistent across all imaginable scenarios. And yet, within that grand impartiality, there is something profoundly intimate, our participation in it. Every observation we make refines the universe's own self-description. Every question adds a line to its informational record. Through us, matter reflects on matter, energy becomes understanding, the cosmos studies itself. This self-reference may be the most striking feature of all. The laws of physics permit structures complex enough to contain models of those laws. Brains, computers, civilizations, each is a small mirror reflecting the whole. If continuity is the universe's foundation, consciousness is its echo, a local phenomenon that knows the global truth of persistence. When scientists look toward the far future, they know that humanity, like every species, is temporary. But the knowledge we generate, once expressed in matter and energy, becomes part of the universal archive. Signals from our instruments, photons from our cities, data encoded in radio waves, all will travel outward indefinitely, fading but never truly vanishing. They will join the sea of cosmic information, indistinguishable but conserved. In this way, existence folds our fleeting moments into its enduring pattern. The laws that shaped the first atoms will shape the last. Between them lies the vast tapestry of transformation, a story written in fields, particles, and the silent grammar of mathematics. The end of existence, then, is not an event to come, but a boundary of language. We call something an end when we can no longer follow its transformation. Physics reminds us that the transformation continues whether we see it or not. The universe, by its own rules, cannot stop being. And so the work of science, far from dispelling wonder, renews it. Each discovery peels back a layer of complexity to reveal a deeper simplicity beneath. A simplicity that says, in every equation, that existence endures. If there is a single thread running through every century of scientific discovery, it is the recognition that nature is reliable. The deeper researchers probe, the more they find that the universe does not contradict itself. Each new layer of understanding fits into the layers below it. Apparent exceptions resolve into broader rules. This reliability is what allows science to exist at all. It is also what allows the cosmos to persist. The same stability that lets electrons circle nuclei without collapsing allows stars to shine steadily, and galaxies to hold their shape for billions of years. Those constants of nature form the quiet scaffolding of reality, invisible, unchanging, and universal. If one asks what keeps existence from unraveling, the answer lies here. Conservation of energy, symmetry of space, invariance of law. This permanence does not make the universe rigid. It makes it trustworthy enough for change to flourish. Because the rules remain stable, matter and energy can explore every possible configuration. Planets, oceans, DNA, language, and thought, all are experiments conducted within that stable framework. Each new pattern expresses the same underlying continuity in its own local dialect. In this sense, every living being is a microcosm of the cosmos. The metabolic cycles that sustain life mirror the thermodynamic cycles that sustain stars. The neural networks that think and remember reflect the cosmic web's interconnections. The same mathematics that describes diffusion of heat applies to the spread of ideas. The boundary between physics and life begins to dissolve. Both are manifestations of organized change. That continuity is why modern cosmology often feels less like an account of beginnings and endings and more like a chronicle of transformation. Even the Big Bang, once thought of as a singular creation event, is now understood as a phase transition, an unfolding of conditions already implicit in the fabric of space-time. What looks like a sudden start is, mathematically, a smooth continuation beyond what we can yet observe. Future theories of quantum gravity may extend that continuation seamlessly. Perhaps the universe oscillates through cycles of contraction and expansion, as Penrose and others have suggested. Perhaps it expands eternally, spawning new regions through quantum fluctuations. Whichever description proves most accurate, they share a single feature: no true boundary. Existence curves back into itself like a closed equation. For scientists, that realization carries a quiet comfort. It means that the universe is not a temporary accident. It is a necessary expression of its own laws. Those laws are timeless because time itself is one of their consequences. The equations that describe change must themselves stand outside of it. At the deepest level, physics reduces to relationships among quantities that never vary. The numbers change. The form of the relationship does not. It is this unchanging relational structure, not any particular substance or event, that defines what is. When matter decays, when stars collapse, when galaxies fade, the structure remains. It can be written differently, but never undone. This view alters how one thinks about endings. An ending is no longer destruction. It is the moment when one expression of relationship gives way to another. The hydrogen that powered a star becomes carbon that seeds a planet. The calcium that built a skeleton becomes mineral in the soil. Even the photons radiated by those transformations continue to interact with other matter across cosmic time. The exchange is infinite. That infinite exchange links every scale of existence. When a person looks at the night sky, the light entering the eye was emitted before life began on Earth. It has traveled through the same physical laws that now govern the neurons decoding it. The observer and the observed share ancestry in those laws. In that sense, observation itself is reunion, a small rejoining of dispersed elements across time. The same principle extends to knowledge. Each discovery does not replace what came before, but clarifies it. Newton's gravity was not wrong. It was local. Relativity refined it. Quantum mechanics refined relativity in its own domain. Science moves forward not by discarding the old, but by enclosing it within broader context. Existence, too, seems to work that way. Every stage encompassing and transforming what preceded it. Even if we imagine a future when the universe has cooled to near absolute zero and matter has thinned beyond measure, physics suggests that the basic pattern will continue. Quantum fields will still fluctuate. Virtual particles will still appear and vanish. The same conservation principles will still govern every exchange. There will still be a grammar, even if no one remains to speak it. And from that grammar, something new could again emerge. Quantum tunneling might create regions of false vacuum that inflate into new universes. In them, new constants could define new histories, each an echo of the last. The cosmos would remain an infinite recursion of possibility, exploring its own equations without exhaustion. In that endless recursion, our brief era, the few billion years of starlight and life, is not insignificant. It is the universe perceiving itself through temporary eyes. The light we study is the same light that shaped our atoms. The thoughts we form are arrangements of the same matter that composes galaxies. To know anything at all is to participate in the continuity that has no outside. Physicists often end their lectures with humility. They know that their models will change, but they trust that the underlying consistency will not. That trust is earned. Every experiment, every observation so far confirms the same set of symmetries. From the quantum scale to the cosmic, the music of reality plays in key. What remains, then, is to recognize that continuity is not monotony. The universe never repeats exactly. It reuses its own ingredients in endlessly inventive ways. Each repetition introduces variation. Each variation enriches the pattern. That is what we call history, evolution, progress. So the universe may expand forever, or contract or spawn new offspring of space-time. But in every case, the essence remains unchanged. Conservation, relation, transformation. Existence, viewed through science, is a single law expressed in infinite forms. And if one asks what comes after all forms have changed, the only honest answer physics can give is more change. The process is its own continuation. That recognition does not demand belief, it invites observation. Every photon, every atom, every heartbeat testifies to it. As long as there is motion, and physics tells us there always will be, the story goes on. If there is a lesson written across the long history of the universe, it is that everything changes, and yet nothing is ever truly lost. Each atom, each photon, each unit of information traces a continuous thread through transformation after transformation. The forms alter, the arrangements evolve, but the total story remains intact. The cosmos conserves itself. From the smallest vibration of a quantum field to the swirl of galaxies, hundreds of millions of light years across, the same laws hold. That constancy is what allows a time to exist at all. It lets the universe remember itself. When we measure ancient light from the cosmic microwave background, we are not merely seeing a remnant of the past. We are reading the present state of an unbroken equation that has persisted for nearly 14 billion years. In that equation, the boundary between past and future blurs. The mathematics of relativity does not privilege one direction of time over the other. It only records change. The arrow of time we experience arises from entropy, from the flow of energy into ever wider dispersal. Yet even that flow is part of balance. The energy that diffuses does not vanish. It becomes radiation, background, potential. The end of one order becomes the foundation for the next. Everywhere we look, this principle of conservation turns finality into transformation. The carbon that fuels a cell becomes carbon dioxide in the air. The air becomes part of the ocean. The ocean evaporates into cloud, condenses into rain, nourishes new life. Stars perform the same alchemy on a grander scale, fusing elements, releasing light, scattering matter, shaping the chemistry of future worlds. The pattern repeats endlessly. Creation through change, endurance through motion. To a physicist, this cycle is not sentiment but symmetry. It is embedded in the equations of thermodynamics and quantum mechanics alike. When one system loses energy, another gains it. When one state collapses, another forms. The sum remains constant, the details ever new. That duality, permanence of principle, impermanence of form, is what gives the universe its beauty. At the heart of that beauty lies the idea of information. Every interaction, no matter how small, alters the cosmic record. Particles scatter, photons exchange momentum, gravitational waves ripple through space. Each event adds another layer to the universe's self-description. Nothing escapes the accounting. even in the most extreme conditions, inside black holes at the edge of cosmic horizons, information is not destroyed but redistributed. The holographic principle ensures that reality keeps its memory. For human observers, this truth carries a quiet comfort. It means that the universe is not fragile. Its continuity does not depend on any particular configuration. Whether matter coalesces into galaxies or disperses into dust, the underlying laws remain unbroken. We ourselves are temporary arrangements of that law, transient but not trivial, for through our awareness, the universe recognizes its own persistence. Consciousness, in this view, is a natural phenomenon, the organization of matter so complex that it can model itself. When we think about the cosmos, we are the cosmos thinking. When we study its history, we are its history becoming self-aware. That self-reference may be fleeting in time, but it is eternal in kind. Wherever conditions allow complexity, the process can begin again. So, the story of existence has no punctuation mark called the end. It continues through transformation, through the reshuffling of matter and energy, through the ceaseless conversation between order and possibility. The universe's rhythm is not linear, but cyclical, not finite, but regenerative. Even if our particular corner grows dark, light will appear elsewhere. Even if our species fades, awareness will rise again in some new form. From this perspective, the silence that awaits at the farthest future is not oblivion, but equilibrium. It is the universe's long exhale, a state of near-perfect balance in which everything that can happen has happened, and the laws themselves rest. Yet, even in that rest, quantum fluctuations will stir, and from one of them, perhaps, a new cosmos will unfold. The process has no author, no conclusion, only the endless logic of continuation. When physicists write their equations, when astronomers map the sky, when any curious mind looks outward and inward at once, that process is alive within us. We are part of its continuity, brief witnesses to its harmony. Our lives, though small in scale, are expressions of the same symmetries that govern galaxies. The breath, the heartbeat, the movement of thought, all are tiny echoes of cosmic motion. The end of existence, then, is not something to be awaited or feared. It is a limit that never arrives, a horizon that recedes as understanding grows. Existence does not stop, it transforms. The pattern goes on, conserving, evolving, unfolding in forms beyond counting. And so the final truth of physics, as far as we can see, is also the simplest. Nothing is ever truly lost. Energy changes shape, matter changes state, awareness changes vessel. But the sum of all that has been, is, and will be remains constant, an eternal equilibrium of being. That constancy is the quiet heartbeat of the cosmos. It pulses through the birth of stars and the cooling of worlds, through the rise of thought and the silence that follows. It will pulse still, long after every light we know has gone out, carrying forward the same law that began it all. And somewhere, sometime, that law will express itself again, as light, as motion, as consciousness, as the simple, enduring fact of existence continuing to be. When physicists study the foundations of the universe, they often find themselves drawn toward the same paradox that confronts philosophers, the relationship between mind and matter. For centuries, science and consciousness seemed to belong to separate realms, one dealing with the measurable, the other with the subjective. Yet, as physics deepens, that distinction begins to dissolve. At the smallest scales, reality behaves as though the act of observation matters. In quantum experiments, particles do not have definite positions or velocities until they are measured. They exist in superposition, clouds of probability, until interaction forces a particular outcome. This does not mean that consciousness creates reality in any mystical sense. It means that interaction, the exchange of information, defines what is real. To observe something is to become entangled with it. The observer and the observed form a single correlated system. This insight has changed the language of modern physics. Rather than speaking of objects, scientists speak of relationships, quantum correlations, entanglement networks, informational exchange. The universe is not a collection of things but a web of interactions. And when that web grows complex enough to model itself, we call the result consciousness. From this perspective, awareness is not a ghostly property added to matter. It is what matter does when it becomes able to process information about itself. The same physical principles that allow atoms to bond or light to reflect also allow neural circuits to integrate data and generate experience. Consciousness is a natural consequence of information flowing through matter under the laws of physics. This view, sometimes called the Physicist information model, finds support across several fields. Neuroscience measures consciousness in terms of connectivity and integration. Information theory quantifies it as the number of independent bits required to describe a system's state. And quantum theory shows that at the deepest level, everything that exists is information expressed as energy and structure. From quanta to thoughts, the difference is scale, not kind. In that light, the universe itself can be seen as a vast informational process, a cosmic computation unfolding across space and time. The equations of physics are its syntax. Particles and fields are its symbols. Events are the results of its ongoing calculation. Human minds are local regions of that computation complex enough to represent the whole. When we think about the universe, we are patterns of energy simulating the larger pattern that produced us. The philosopher and physicist David Bohm hinted at this unity when he described the implicate order, a deeper level of reality in which all things are enfolded within one another. In his view, the world we experience is the explicate order, the unfolded manifestation of this deeper wholeness. Consciousness and matter are not separate entities, but different expressions of the same underlying process of unfolding and enfolding information. Quantum field theory, though formulated independently of philosophy, points in the same direction. It tells us that what we call particles are not tiny billiard balls, but excitations in continuous fields that fill all space. These fields overlap and interact, exchanging information in ways that transcend ordinary boundaries of space and time. In this continuous medium, there are no absolute separations, only degrees of correlation. If awareness arises from information exchange, then consciousness is already implicit in the fabric of reality. Modern physics does not say that electrons think, but it does say that they communicate. They respond to fields, to forces, to probabilities, to patterns. They act and react according to rules that ensure the preservation of information. And, from the sum of those interactions, complexity grows. From complexity, awareness becomes possible. From awareness, understanding arises. In this chain, consciousness is not an anomaly. It is the latest expression of the universe's tendency to preserve and process information. Every step in cosmic evolution, from the formation of atoms to molecules to cells to minds, has been an elaboration of the same pattern. Information organizing itself into forms capable of sustaining further organization. This is what physicists call emergence, the appearance of new properties that cannot be predicted by studying parts in isolation. If information is conserved, as quantum theory insists, then awareness itself participates in that conservation. The specific patterns of thought that define an individual may vanish, but the structure that allowed those patterns, the informational capacity of matter, remains. In that sense, consciousness is not an isolated spark. It is a recurring property of the universe whenever conditions align. Wherever complexity reaches the threshold of self-reference, awareness will bloom again. This continuity reshapes how we understand our place in the cosmos. For much of human history, the universe appeared indifferent, vast, and silent. Yet physics reveals a deeper connection. We are not outside observers, but participants in a process that includes us. The laws we discover through experiment are the same laws that make us capable of discovery. Awareness is not an accident. It is one of the ways the universe expresses its coherence. Information theory gives this insight mathematical precision. Every physical system can be described by its entropy, a measure of the information required to specify its state. Consciousness, in turn, depends on the ability to integrate information across many subsystems simultaneously. The brain achieves this through networks of neurons exchanging signals. The universe achieves it through the entanglement of fields and forces. In both cases, meaning arises from connection. This understanding dissolves the old boundary between inner and outer. The patterns of thought that form a human mind are local versions of the same logic that governs galaxies. Our memories are arrangements of matter and energy that obey the same conservation laws as stars. Even emotion, that subtle modulation of experience, is a rearrangement of physical states, part of the same continuum that drives planets, atoms, and light. Physicists like John Archibald Wheeler, who coined the phrase "it from bit," captured this elegantly. He imagined a universe in which every it, every particle, every field, every event derives its meaning from binary choices, from information. At the deepest level, the universe is not made of substance but of questions and answers, yes and no, interaction and response. In such a universe, consciousness is the mirror in which these informational processes reflect. This does not make humanity the center of existence. Rather, it places us within an unbroken hierarchy of complexity, one node in the vast network of awareness that the cosmos builds through its own dynamics. If stars can give birth to the elements of life, and life can give birth to mind, then the line between physical and mental, between matter and meaning, is one of degree, not kind. To understand this connection is to see continuity in its fullest sense. Matter, energy, and information form a trinity that sustains existence. Consciousness is their resonance, the echo of the universe understanding its own laws through living systems. When awareness fades, its ingredients do not vanish. They return to the web that produced them, ready to participate in new configurations of thought elsewhere, somewhen. The physicist Erwin Schrödinger once wrote that consciousness is a singular of which the plural is unknown. He meant that at the deepest level, all minds may be expressions of one universal awareness, differentiated only by perspective. Whether or not that is literally true, physics supports the metaphor. Everything is connected through entanglement, through the continuity of information, through the shared substrate of law. No part of the universe is ever entirely alone. The implications are profound. If consciousness is a natural product of complexity, and complexity is a natural outcome of physics, then awareness is woven into the cosmic process from the beginning. The potential for perception exists wherever matter and energy exist. The emergence of mind is not a deviation from the laws of nature, but one of their most intricate results. This means that when we look outward at the stars, we are also looking inward at the conditions that gave rise to thought. The geometry of space-time, the behavior of fields, the fine-tuned constants of nature, all of them conspire to make awareness possible. Our capacity to ask questions is not separate from the fabric of the cosmos. It is one of its properties. Seen in this light, the end of existence becomes less a cosmic catastrophe and more an abstract limit. Even if our universe grows cold and diffuse, its information will persist, encoded in the faintest ripples of quantum fields. If another universe arises from those ripples, the potential for awareness will arise with it, because the laws that allow it are eternal. Consciousness is not the exception to continuity. It is its finest expression. Some physicists speculate that the flow of information through conscious systems may even contribute to the universe's overall dynamics. Though such ideas remain speculative, they capture a poetic truth. Awareness and the cosmos are part of the same self-consistent story. One cannot truly end without the other because they are two sides of a single process. Existence knowing itself. In that sense, the fear of the universe's end, or of consciousness ceasing, softens into understanding. The atoms that make a thought are immortal on cosmic timescales. The laws that shape experience are immutable. What changes is configuration, the dance of information within the field of possibility. When that dance takes the form of a living mind, the universe momentarily contemplates itself. When the dance changes, awareness redistributes into other patterns, continuing the conversation of being in new dialects of matter and energy. Every wave of creation, every spark of thought, every glimmer of understanding is part of the same eternal feedback loop. The cosmos looking back at itself, recognizing its own continuity. And perhaps that is the quiet truth science has been approaching for centuries, that existence is not just persistent, but self-aware in principle. Through the physics of information, the universe possesses the means to remember itself, to measure itself, to evolve in response to its own state. Awareness, wherever it appears, is simply the local experience of that global capacity. If so, then there can be no ultimate separation between the mind that wonders and the universe it wonders about. Both are expressions of the same invariant law, the conservation of information, the preservation of connection. We are not observers peering into a foreign cosmos. We are the cosmos becoming aware of its coherence. And, as long as that coherence endures, as long as energy and information continue to flow, as long as the equations hold, awareness will find new forms. It will arise wherever the conditions allow, just as light arises wherever there is potential difference. Consciousness is not confined to us. It is a property of existence itself. So, when physicists speak of the end of existence, what they truly confront is not annihilation, but transformation, the reshaping of awareness into new expressions. The end of one pattern is the beginning of another. The music pauses, but the melody remains written into the fabric of reality. And perhaps, far in the future, when new universes are born and new minds awaken beneath unfamiliar stars, they too will look outward and feel what we feel now. Wonder at the immensity and recognition that they are part of it. They will ask the same questions, trace the same patterns, and rediscover the same conclusion: that existence in all its forms is one unbroken continuity, matter becoming meaning, energy becoming awareness, law becoming life. The universe will continue its endless act of remembering, and consciousness, wherever it emerges, will continue to be its voice. Because in the deepest sense physics has yet revealed, there is no edge between knowing and being. There is only the eternal unfolding of information, endlessly aware of itself.